Okay. No.
Okay, can online people hear me okay now? Okay, right, I guess, is someone monitoring the chat? Okay, great, okay, yes, let me know if there's any questions online. I'm not sure if people speak out.
Oh, maybe you should just change tab and go to the presentation.
Oh, yes, how do I do? I'll place minimize. Okay.
Yeah.
Right. Okay, so I wasn't quite sure what to include and how the timings are going to work. So, okay, so I prepared kind of a lot of topics, but kind of feel free to tell me to speed up or slow down, and yeah, I'll sort of work things out. So, I mean, like most of, well, I would start off talking about some of the theory. So this is based on sort of like a lecture course I gave like a few years ago, which is a sort of 30-hour lecture course. And so I sort of crammed it down into about 3 hours. So you can sort of anticipate where the problems are going to be. Okay, but I've tried to kind of get rid of all kind of technical details and really just kind of convey the key ideas. Okay, so after all of this, you're going to be worn out. So I'll just show some pictures for the last sort of 20 minutes or so. So that's at least is the provisional plan. Okay, so I'll start off with some motivation. I probably don't really need to motivate it as you asked me here. So, but still, let me to go like, why do we expect the optimal transport to be a good distance? Okay, so I think the first place to start is, well, what's the first thing we would kind of do? If we had like, two images, the most naive thing we could do is maybe look at Euclidean distance. So let's look at the Euclidean distance between two balls, the red ball and the blue ball. Well, if we take away the blue ball from the red ball, this is kind of what we have in mind, right? So the distance between the red ball and the blue ball, in some sense, just the area of the non-overlapping regions. Okay, so we can now think of parameterizing this. So maybe we fix the red ball, and we think of moving this blue ball a distance r, say horizontally, and then we sort of say, okay, so then what's the distance as a function of r? Okay, it'll look something like this. Okay, so what we can notice in particular is once r is bigger than the radius of the ball, right, the L2 distance is constant. Why is this a problem? Well, let's imagine we want to optimize r. Okay, so we do gradient descent. So now we choose an initial value of r, and we compute the gradient of the L2 distance, and it's flat, right? So it's kind of not telling us, and of course, right, it's physically the L2 distance isn't really the right thing, right? It's not. There's no sort of modeling motivation for it. Okay, so what's a Lagrangian base of distance? Now this will be, you understand, so taking away the blue ball from the red ball as being this vector field, which just sort of shifts the blue ball in the direction of the red ball. Okay, and so now we'd say, well, if you look at sort of, a Lagrange-based distance, okay, so an example would be the Wasserstein distance. This would just pay a cost proportional to the size of this vector field. Okay, so this now is much nicer because if we parameterizing again by r, okay, we see that it doesn't matter how big r is going to be, right? The distance is always just going to scale linearly. Okay, so this is kind of nice. Okay, so that's kind of my motivation. I guess now I'm going to go and talk a little bit about sort of the formulations of optimal transport. I'll start off, I guess, in the historic order with Monge. Okay, so we have two probability measures, mu and nu. So there'll be probability measures on the space x and the probability space y. Okay, so I guess I warn you now that I'm going to abuse my notation. So most of the time these are going to be probability measures. Sometimes there'll be densities of the probability measures. Okay, so we also assume we have a cost, c of xy, and this we understand as being the cost of moving 1 unit of mass from x to y. So typical examples are going to be, if c of xy is equal to the Euclidean distance between x and y, say, or that's probably that or x minus y all squared are probably the two most common choices. Okay, so if we're given a function t from x to y, the cost of moving the mass given by this sort of map t is just the integral of c of x, t of x integrated over mu. Okay, so we can, if we sort of try to write this down as our optimal transport problem, we can see, okay, We can see where the new dependence is, but okay, but what about the new dependence? Okay, so the new dependence comes in terms of a constraint on the map T. So in particular, we want to move mass from, okay, once the amount of mass we want to move is mu of x, we want to move this from x to t of x, and then after sort of this rearrangement, we should end up with the measure nu. Okay, so mathematically, we sort of write this as the amount of mass at B should be the amount of mass in the pre-image of T under the measure mu. So, okay, this is probably going to be great for the online people, but the picture is kind of, okay, so we have space X, we have space Y, we have our map T. So if I pick a set B here, then okay, this is going to correspond to some T inverse B. And all I say is that the mass under, so this is Euler's here, Euler's here, the mass under nu on the set B has to be the same as the mass under mu of the set T inverse B. Okay, and okay, so in this T inverse, right, this is kind of understood in this set theoretic sense. So I'm not saying that T is invertible, right? This is the set of points which maps to B. Okay, so okay, so most of the pictures in this talk weren't produced by me, which is why most of the pictures in this talk are actually quite good. This is one of the few images that I produced that actually I'm quite proud of, right? So I don't know, it looks quite pretty here. Right, so this is the measure mu, this is the measure nu. Okay, and I've just sort of colored it so you can kind of see how after rearrangements, the T is kind of distorted this this measure. Okay, so there can be many such maps T satisfying this sort of conservation constraint. There could also be none. So when there are lots of different measures, then of course we choose the best one. This would mean that our sort of Monge optimal transport problem is to minimize the cost of moving from x to t of x, okay, integrated with respect to mu of x, and we minimize this over the set of transport maps which push forward mu onto nu. Okay, so I'll sort of say this sort of quite early because I guess it's particularly important. So the Wasserstein distance. So if we choose our cost to be some p to the power of Euclidean distance, right, then we will call this sort of the Wasserstein distance. So in particular, if we just substitute in c of xy, so x minus y to the p, right, then of course we have to take the pth root. Right, this is kind of the well-known Wasserstein distance. The other special case of interest is when c of xy is just a metric. In that case, we would call this sort of the earth mover's distance. Right, so of course, when p equals 1, right, the 1 Wasserstein distance is an earth mover's distance as well. Okay. Yeah, and okay, so this is the Monge form of optimal transport. So maybe the first question to ask is, do transport maps always exist? And the answer to that is no, they don't always exist. So you have a very simple example here where there's no transport masses. So here our measure mu is 2 Diracs of mass a half, and our target measure nu is 3 Dirac masses of mass a third. So you can see there's no way to get to take mass from mu and rearrange it according to nu, right? The only way to do this is to split mass. Right, so we can't do that. Solution is to split mass, right, which brings us to the Kantorovich formulation, which is in some sense a relaxation of the Monge formulation. Okay, so now we let pi of xy be the amount of mass that moves. Okay, so pi of xy is the amount of mass moving from x to y, right? And so okay, so in the previous example, a natural solution will be to move a third of the mass from the first point, and then move a sixth of the mass from the first point to the second point, okay, then a sixth of the mass from the second point to the second point, and a third of the mass from the second point to the third point. Okay, so then we still have the constraints. So the amount of mass which leaves from x should be the amount of mass that which we have at x. So the amount of mass leaving from x, if forgive my sort of abuse of notation, is going to be given by pi of x onto the whole of y. Right, so this has to be equal to sort of mu of x. Okay, and similarly, the amount of mass arriving at y should be the amount of mass that's sent from everything in x to y. So this leads us to the second constraint of being sort of pi of xy has to be equal to mu of y. Again, if you forgive my constraints. Of course, you can write all this sort of properly in sort of, sort of a weak form. Yeah, or in terms of sort of sets, right? Okay, so we let pi of mu nu, this is the set of probability measures on the space x cross y, which satisfies these two conditions, right? So I'll often say that this condition here is a condition on the first marginal of pi, right? So the first marginal of pi should be equal to mu, and this condition here is a condition on the second marginal pi. So the second marginal pi should be equal to nu. Okay, so with that sort of notation in mind, we can define the Kantorich form of optimal transport, which is just to minimize c of xy with respect to transport plan pi, where we minimize over all plans pi, which have the first marginal mu, second marginal nu. Right. I'm trying not to go too quickly. The problem with slides is that the temptation is to keep pushing the button at a time. Right. Okay, so I wanted to, again, just to make an early connection to sort of linear programming. So I believe Kantorich is kind of regarded by some as one of the founders of linear programming, kind of for exactly the reason that optimal transport is really a linear programming problem when written in the Kantorich form. Okay, so if we start off with our sort of Kantorich form of optimal transport, okay, so we're minimizing c of xy, d pi of xy. Okay, and let's just, I guess at the level of the computer, everything is discrete, right? So let's assume that our mu is given by a sum of Dirac's, and our nu is also given by a sum of Dirac's. Okay, in that case, we can really think of this pi as just being a matrix, right? So pi of pi of xy is just the amount of mass moving from x to y, and so we can sort of index everything, go from xi to yj. Okay, so we end up with a sort of of a sort of set. Pi of mu nu is a set of n by n matrices. Okay, and then we have the constraints. So the constraints tell us where the total amount of mass which is moving from some x and the amount of mass that's moving to y. Well, this is just going to be the column and row sums, right? So essentially, we're just looking at a set of matrices where everything has to be sort of non-negative, and then the rows and the columns have to sum to either, in this notation here, it'll be either the p or the q. Right. Okay. So then the objective function itself. So this essentially then is just multiplication. Right, so what we really end up with is that the objective is just the multiplication of the matrix C, okay, where this, okay, the ijth entry of this matrix is just the cross between xi and yj, okay, and then pi is, okay, as I said before. So this now is a linear objective, okay, and then this set pi here, you can see this is convex. Right, so this is a linear program, okay, and so of course a lot of the theory we expect from linear programming comes through. So in particular, if you know about linear programming, right, then there's a dual form, right? So of course there's a dual form for optimal transports. Right. Okay, so I call this section basic theoretical results, and then I kind of realized that's probably not. The word basic probably isn't the right word to use here. So, okay, so I'm going to start off, I guess, with some, maybe fairly sort of elementary, okay, I guess I'm using elementary now rather than basic. So observations like between the Kantorich and the Monge formulation. But then I also kind of include in this situation things like the dual form. I'm going to look at optimality conditions, so things like the Knott-Smith optimality criteria, right? And I guess, wouldn't necessarily say that was basic, but it's sort of, I want to sort of group everything together. Okay, so the first thing I wanted to say then is the sort of relationship between the Monge and the Kantorich form. And so in particular, the Monge formulation kind of provides an upper bound for the Kantorich formulation. Okay, and Okay, and this is because any transport map, so if you have a transport map in the Monge formulation, this induces an optimal transport plan for the Kantorowicz formulation. Okay, so to see this, if we let T of xy be a transport map, okay, so it just satisfies this sort of mass conservation, then we can define this pi as being the essentially the measure which is raised to the graph of T. Again, maybe yeah, sorry for the people online, but I guess people on that side of the room are also kind of equally disadvantaged if they're only writing this right here. So if we have, if this is sort of x, this is y, you know, we have some sort of transport map T. Right, so our measure mu lives on this axis here. Our measure nu lives on this axis here. Then then this pi will live on this. Okay, this is on the graph here. So if you imagine, okay, maybe mu looks like, you know, a Gaussian. Okay, maybe nu can also, well, nu can maybe look like a double Gaussian. Okay, so then this there's going to be kind of more mass around here, and okay, I guess my transport, my T is wrong, so the picture sort of breaks down. But okay, the point is, okay, one can kind of check that this this pi here is going to have the right sort of marginals. Okay, so in particular, this pi here is in the set of, you know, capital pi of mu and nu. Okay, it's also fairly easy to check that the cost of this transport map T is equal to the cost of this transport plan pi. Okay, and so in that case, if we take the minimum over all these T's, right, then this is going to, and then take the minimum of all these pi's, okay, then we know the minimum of the T's is going to be sort of bigger than the minimum of the pi's, right? Because any T in here induces a pi in here. So of course this is potentially a much bigger, sorry, this is potentially a smaller set, this is potentially a much bigger set, right? So the minimum on the right hand side has to be smaller. Okay, the converse also holds, but this is when the transport plan pi can be written in the form of a transport map. In that case, then everything kind of goes back through, and you end up with an equality here, and that means the Monge and the Kantorowicz forms coincide. Okay. Right. Okay. So I guess the first of, you know, really theoretical result is the existence of transport plans. Okay, so some technical conditions. So x and y Polish, C is lower semi-continuous. Then the proposition says that between any two measures, mu and nu, there exists a solution to the Kantorowicz's optimal transport problem. Right, so there exists some optimal pi, and this actually is fairly straightforward to show. So it's essentially the standard sort of, you know, calculus of variations argument. Compactness plus lower semi-continuity gives existence of minimizers. Okay, so compactness, we get to compactness through tightness. Okay, so we want to show that this set here, pi mu nu, is tight. So to do this, you know, we fix some delta. Okay, so, and we choose sets k and l, okay, that are compact and such that the majority of mass with respect to mu and nu is contained, okay, in k and l. Okay, so up to delta. Right, we know the mass is all in the sets k and l. Okay, and this just follows because mu and nu are both probability measures, right? So this kind of has to be true. Okay, so then we pick any plan in the set of couplings. Okay, and we just look at what the measure of the set is. Okay, well, outside of k cross l. So we can bound this quite easily by looking at well, I guess let's just write this down. So if this is x, this is y, right? Then we have the square So this is going to be my set K. This will be my set L. Right, so if I want to know what's outside of this square here, right, well, I can bound it by looking at what's in the kind of above and below this line, and what's to the left and to the right of this line. Right, I'm going to count everything at least once. Okay, in some areas I'm even going to count count twice. Okay, but once I have this bound here, right, you can see, well, this is just going to be equal to the second marginal pi. This is going to be equal to the first marginal pi because I'm sort of integrating out x, integrating out y. Okay, so yeah, so I have, okay, this is just nu of y less L, and this is mu of x less k. And so, of course, these two things are both bounded by delta, so everything's less than 2 delta. Okay, so this means now that my set is tight. Okay, I should check closure. So if I have a sequence of pi n, okay, in my set of couplings, right, that's converging weak star. Okay, this, well, by definition, means I have this convergence here. Okay, so if I just choose my f now such that f of x, y only depends on x, right, then this will mean that, okay, so I then would know that this thing here is just going to be equal to the integral of f of x with respect to mu of x, right, and then so of course, right, this means then that well, the first marginal pi has to be mu, and you know, it's the same argument for the second marginal. Okay, so I have closure. Okay, so now I can invoke Prokov's theorem. So this is tightness implies the closure is weak star compact. So I know I'm closed. Okay, so I know I'm weak star compact. Okay, and I guess I didn't sort of show it, but then one can also kind of check that that your objective function is going to be lowest and continuous. Well, in fact, I mean it's linear, right? So it's, of course, it's continuous. Okay, so this then means that we have an existence of an optimal transport plan. Okay, any questions up to now? Boy, I don't know when a good time to break is, but just sort of let me know when you think people need to, you know, have a rest. Okay, so the next thing then I want to go to is duality. Okay, so for duality, we have to introduce the set phi c. So this is going to be the set of functions which are L1 with respect to mu and L1 with respect to nu, such that the sort of pointwise addition, so phi of x plus psi of y, is less than or equal to the cost between x and y. Okay, then we have the objective j, which is just going to be the integral of phi with respect to mu and the integral of psi with respect to nu. Okay, then duality just says that the optimal transfer problem is equal to the maximum of phi and psi in this sort of set here of j, right? So I think on the next slide I have kind of a very simple sort of sketch proof of this. Okay, yes, this is a formal proof, so I'm not kind of worrying too much. So I'm going to invoke, you know, essentially a maximum principle, and so okay, and I'm not going to worry about stuff, you know, checking the conditions.
What's the intuition about that?
Good question. There is ways. Okay, so there's the nice, well, the way Villani sort of describes this is in terms of like the shipping problem. So he would sort of, right, so he would sort of imagine this. Okay, so here, I guess if you're doing this sort of like, you know, if you're running a delivery company, right, you have a cost of transporting from X to Y, right? So this is kind of clear how this problem comes up. This problem here is kind of, you imagine sort of you're just doing the unloading and sort of loading. So here, instead of sort of paying for the cost of the shipping, right, you pay for a cost of, you know, you pay phi of x to load your ship at point X, and you pay the cost of psi y to unload your ship at, you know, at Y. And so I guess what's sort of nice about this is that you can kind of design your costs in such a way, right, that you're not going to sort of lose any money. So I guess, the shipper, he perhaps doesn't want to charge people, based on the distance that he's going to, that their letters are going to move. He just wants to charge them at the port, right? But he can sort of, choose a cost, which means that, so the person, I guess, paying this cost is going to be happy because the total cost that they're going to pay is going to, so they pay phi of X putting their letter on the ship, they pay psi of Y for taking it off. That's going to be less than the cost of actually going between X and Y. So they should be kind of happy. And of course, the person who's actually doing the shipping is going to be happy because it's not going to cost him any more overall because he can sort of choose this phi and this psi such that it still achieves the minimum. So is that sort of,
Yeah.
okay. Okay, so you can kind of see where this sort of proof comes from sort of analytically. If we let P of X be the projection onto the first marginal, so P of XY is equal to X, Py of XY is equal to Y, is the projection onto the second marginal. Okay, then we can write this sort of constrained optimization problem here. So we're taking the sort of minimum of C of XY d pi of xy over all pi's with the right marginals. Right, we can instead take the minimum over all pi's, just probability, positive probability measures on the space x plus y, and instead we sort of put in the constraints into the objective. We're taking the supremum over phi and the psi. Okay, such that so you can see here now, if our marginals are not exact, so if the first marginal pi is not equal to mu, then I can send my psi here off to plus infinity. So this whole thing here is going to be plus infinity. Of course, I want to take the minimum over pi. Right, so the choice of the minimum here is going to mean that this thing here is never going to not be zero. Right, whenever this thing here is not zero, then this supremum is going to be plus infinity. Okay, so I can sort of absorb. I can make this, essentially an unconstrained optimization problem, but with like an objective that's just going to take the value plus infinity where the constraints aren't satisfied. Okay, I can rewrite this sort of slightly by, so I keep my integral of phi with respect to mu, I keep my integral of psi with respect to nu, and then I just sort of absorb this sort of first marginal in here by just having c of xy minus phi of x minus psi of y, all integrated with respect to pi. And now this is kind of where I become a little bit formal because I switch this sort of the minimum and the supremum around. And once I do that, right, then you can sort of see, well, I'm going to end up back with a constraint optimization problem again. But now the constraints are going to be on phi and psi. So in particular, if c of xy is bigger than phi of x plus psi of y, and this is true for all x and y, then the smallest I can possibly make this sort of integral here is going to be 0, right? Because pi is positive and this thing here is always positive, so the best thing I can do is just set pi as being equal to 0 everywhere, and so when phi plus psi is less than or equal to c, right, I get this here. On the other hand, if at any point psi of x plus psi of y is strictly greater than c, right, then this integrand here is going to be sort of negative at that point, in which case I can send my pi going off to plus infinity. Okay, so then this whole thing here is going to end up being equal to minus infinity. Of course, if I want to take the supremum, I'm not going to choose a pi which does that. Okay, so what this means I end up with is this supremum here is over the integral of psi plus the integral of phi, okay, with the condition on psi plus psi being less than or equal to c. And this was exactly the dual problem that I had on the last slide. Okay. So I'm sorry, so this is kind of like thick and fast, I guess, now. So the next thing I want to introduce is these C transforms. So if I take a function phi from x onto r plus or minus infinity, okay, I can define the C transform. This is now going to be a function from y onto r, and it's just defined as being this okay, so the C transform of phi at y is the smallest value with respect to x of C of x, y minus phi of x. Okay, and then the second C transform is essentially just doing this again, but now with phi c instead of phi. So this is very similar to the convex conjugate, kind of up to some minus signs which kind of float around. Okay, so in particular, so if y is the dual space of x, okay, and C of x, y is just the inner product between y and x, right? Then you end up with minus phi. Take the C transform of minus phi, apply it to minus y, then you end up with the Legendre differential transform or the convex conjugate of phi at y. Okay, where this is kind of the usual thing. So the supremum of inner product of y and x minus phi of x. So they're kind of very similar, right? So, okay, so the point of stating this is to show that it's for these sort of to show the maximizers of the dual form take this form of a sort of C transform pair. Okay, so not only is there a maximizer to the dual problem, right, but this maximizer takes this form here where, so for some phi, right, I can use the second convex conjugate of phi in the first argument and the first convex conjugate in the second argument. So just as kind of a note, this pair here, right, is in the constraint set, right? So actually, I'll show that on the next slide. Yep.
How does phi double conjugate relate to phi?
It can be exactly the same thing. It's just so okay. I have to kind of double check these things exactly, but like with the convex conjugate, right? If you start off with the convex function, like a lower semi-continuous convex function, you take its second convex conjugate, right? You just get the function back again. It's kind of the same thing here. So it might end up being, so if it's, I don't say in case I'm incorrect, but if phi, for example, okay, so again with convex conjugates, right? If it's not lower semi-continuous and convex, I think you get something back like the lower semi-continuous envelope of the function back, and I think you probably get something sort of similar here. But yeah, you're right. I mean, what you could do is replace this with a phi and this with a.
So under what condition, or at least like what's an example of a situation where phi double conjugate are equal to each other? Because for convex functions, like I don't know if you start off with the convex function and you come back.
It would be off the top of my head, I couldn't give you it, but essentially you'd have to kind of, essentially I guess you go back to the remark here and you just have to translate the conditions for the the convex conjugate and put them back in terms of the the C transforms. Okay, so I've got a few slides that are kind of on this sort of sketch proof for this. So the first thing I do is I take any sort of revalued R and any sort of pair in my dual constraint set. Okay, so the first thing I want to notice is if I take the second convex conjugate, right, so this by definition is just the infimum of y, so primum of z of cxy minus czy plus phi z. Okay, so I can make this smaller by choosing a particular z. So if I choose my z to be equal to x, right, so these two terms here cancel, then I get 5x. So the point being that the second the second C transform, right, is going to increase the value of my phi. Okay, and there's kind of a similar thing here. So by definition, the C transform of phi is equal to infimum of x of c of xy minus phi of x. I know my phi is in the constraint set here. Okay, so I know that phi of x plus psi of y has to be less than or equal to c of xy. So I know this thing here is all less than psi of y. So the point now is being that the second convex conjugate, the second C transform, the first C transform, right, increases the value of psi. Right, so what this means then is that if I take my dual form here,
okay, my joule sort of energy, apply it to phi and psi. Right, this is going to be, I can increase it by substituting in the C transforms. And of course, this A here plays kind of no role because it's just integrating out. So I can add A to the first argument, subtract A from the second argument, and everything kind of works out fine. I can also check that the second C transform plus the first C transform, right, this is going to be less than or equal to C of xy. Okay, so this means then that the second C transform and the first C transform are always kind of admissible for the dual problem. Right, and of course, anyway, I didn't add it here, but I could add on A, plus A here, minus A here, and that's not going to change anything. That still be in the sort of admissible set. Okay, so the point now being that I can kind of always assume my optimizing power of this form here.
Right. Okay. So it's sort of I guess enormous standard sort of argument for the calculus variations. We just have to kind of go through a few sort of steps.
So I take a maximizing sequence. This is going to be my phi k and psi k. So these are converging to the supremum. Okay, so now I sort of modify this slightly by looking at the sort of second C transform and the first C transform, and I add on, well, add and subtract some constant A, okay, which I define now. So this is just going to be this value here, and I think I sort of missed this off when I stated the. And yeah, okay, so I kind of skipped over this. So we assume that the cost function here, C, is less than or equal to some C of x plus C of y here. Okay, and this is, I guess like a technical condition which makes things easier. It allows us to carry out this argument. Okay, so anyway, what we have is that this constant here, AK, is is real valued. I didn't check that it's finite, but you can do that. Okay, and perhaps more importantly, we know that psi tilde, okay, has to be less than or equal to C of y. Right, this is just by construction of AK. Right, the psi tilde AK is the first C transform plus AK. Okay, okay, yeah, and so by I can make this thing here bigger, right, by choosing by choosing a particular value of y here, right? So of course then that I can choose my y so that okay, and I can also sort of check similarly that phi tilde, okay, right, this is going to be less than or equal to C of x. Right, so I have kind of a pointwise bound. Right, so what I do next essentially is to truncate. So I take the maximum of psi tilde k x minus C of x and minus L, then I add on C of x here. Okay, so if the maximum is is the first part here, right, then of course I just have psi tilde is equal to psi tilde L is equal to psi tilde, right? But I'm sort of cutting it off so that I know I can always lower bound by CK minus L, and do a similar thing for psi here. And I do it exactly so that I have this these inequalities here. And in particular, if I sort of subtract C of x from the top one, right, I have that minus L has to be greater than or equal to psi tilde K of L minus C of x, okay, which has to be less than or equal to 0. Okay, and a similar thing for psi tilde, right? So what I have now is I have like some sequences which are bounded in infinity, right? So my psi k tilde L minus C of x, right? These are bounded in infinity. So now I can start looking at sort of converging subsequences, right? So in particular, I can sort of assume that we have some psi tilde L. Okay, well, psi tilde L minus C of x and psi tilde L minus C of y, such that psi tilde K of L minus C of x is converging to psi tilde L minus C of x. Okay, I have so for each L I have this. my weak convergence preserves the ordering. Okay, so I have monotonically decreasing sequences in L. Okay, so this is now means I can apply the monotone convergence theorem, and I have some pointwise limits. Let's say psi dagger and phi dagger. Okay, so then if I take my supremum, okay, so I take my dual problem, right? This by construction, right? I know that. Well, okay, so because psi tilde and phi tilde were maximizing sequences, so this was by choice. Then this was because I've increased the value. If I go back onto the last slide here, right? I know my psi k tilde is is bounding from below my psi k l, right? So I've increased the value of the integrals, right? So I've increased the value of j, and then taking L off to infinity. This was the monotone convergence theorem. So at this point here, I'm almost done because I now have this sort of candidate sort of maximizer. I just need to check that this sort of psi dagger and psi dagger are an admissible pair. Okay, and that is true, right? So you can sort of check that this is that the sum, well, for any L, the sum is going to be less than or equal to the maximum of C of x y minus C of x minus C of y, with minus L, plus C of x plus C of y. So when I take L off to infinity, right, the Cx terms also disappear, and I end up just with the maximum. I end up just with the C of xy term here, right? So this is kind of in my constraint set. Yeah, and then that's sort of essentially done. Right. Okay. So there is a second form of duality, which is the Kantorovich-Rubinstein duality. Okay. So for this, we assume that x and y are the same space, and okay. So C is going to be lowest end continuous, as it has been throughout. We define the Lipschitz constant for a function f with respect to the sort of cos C as just being the largest, with x not being equal to y, of fx minus fy divided through by C of xy. Right, so of course, if C is just the Euclidean distance, right, this would just be the normal sort of Lipschitz constant, right? So now, of course, we're dealing, I guess, in a more sort of abstract way with the sort of general cost of C. Okay, so what we have then is that our sort of Kantorovich optimal transport problem. This is now the sort of largest that the integral of f can be with respect to the difference between mu and mu minus nu, where this f ranges over all functions which are Lipschitz with constant less than or equal to 1. Okay, so this form actually gets used kind of in Wasserstein-Ganz, for example. But I kind of included it here because actually it comes up quite a lot in stuff other places as well. So I think it's quite a useful form. Right. Okay. So again, I have kind of like a sketch for the proof. So I ask you to first of all just take my word for three different things. So first of all, I ask you to believe me that the that the C transform of any phi has Lipschitz constant less than or equal to 1. I ask you to trust me that the second C transform of phi is equal to minus phi of C. I've written this. This seems unlikely to be true for all phi, but so maybe it's only true for the optimal phi. But I guess we'll find out in a minute. I wrote these slides, I guess, a couple of weeks ago, and it was like 70 of them, so I've forgotten what's on most of these slides. Now, okay, and then the third thing I asked you to kind of believe me for now is that minus f and f are admissible for the dual problem. Okay, for any f that have Lipschitz constant less than or equal to 1. Okay, so if you believe me, if you believe these three assumptions, okay, then if we start off with the dual form, right, this is going to be equal to the supremum over. Okay, so this is what we've kind of shown before, that I can just assume that my phis are sort of these sort of C transform pairs. Then using condition B, I can substitute in the second C transform, okay, with minus the first C transform. Now I can potentially make this bigger by using A. So because I know, okay, so I know that any sort of pair here is going to have Lipschitz constant, okay, less than or equal to 1. Okay, so this makes it kind of yeah, this set here is potentially bigger. Okay, and then I can use C. So again, I can make this set here bigger because I know now that for any, yeah, so any functions f with Lipschitz constant less than or equal to 1, these are going to be an admissible pair. So of course, when I go from sort of left to right, you know, I have the same thing on both ends. So all these sort of inequalities must be equalities. Okay, and so that, you know, I have that the dual form, okay, is going to be equal to, you know, this form here, say, right, and I know by the previous sort of duality theorem, right, that this dual is equal to the Cantorich form of the optimal transfer problem. Okay, so then I know that the Cantorich form of the optimal transfer problem is equal to this here. Okay, and this J. So J, remember, is just the integral of f with respect to, well, I'll just write it down. Right, so I just have J minus f. F, okay, is equal to integral minus f d mu plus integral of f d nu. Okay, so I guess this then is the integral of f with respect to nu minus mu, which okay is up to a minus sign, is what I wrote in the statement of the theorem. Okay, so what I really have to do now is to show these three facts here. Okay, so to start off with the first thing that I want to know that the C transform of phi is less than or equal to 1. Okay, so I can just sort of, you know, take two arbitrary points. And if I look at the difference between them, okay, so by definition, I can write this as the infimum over w, supremum over z, or c of x w. Okay, so this C transform of x here is going to be, so yeah, it'll be c of x w, okay, minus phi of w, and then the C transform of phi at the point y, okay, with the minus sign, right, it's going to give you minus c of y z plus phi of z. So I want to make this bigger. Okay, so I can make this bigger by choosing a particular w. So if I choose a w, so w, I think I probably choose w being equal to x. But no, sorry, I think I choose w being equal to z. That way these two things here cancel. Right, and then I get, yeah, so yeah, c of x z minus c of y z. Okay, and then this is going to be equal to c of x y. Why is that? I think I must have assumed that c is a metric. Let's check. Yeah, so c here is the first thing is metric. So, okay. Okay, so that then, okay, so of course, you know, if I bring c of x y onto the other side, there's nothing particularly special about doing x and y in that way around. So by symmetry, right, I'm going to have that phi c of x minus phi c of y in absolute value divided through by c of x y is less than or equal to 1. Okay, so then let's look at this case here. Okay, so again, by definition, the second C transform of phi is equal to the infimum over y of c of x y minus the first C transform of y.
Sorry, 1 second. Why? Sorry, what happened during the last inequality there? Yeah.
This here, this. So I assume that c is a metric. Okay. So I guess c of x z is going to be less than or equal to c of x y plus c of y z.
Okay.
So then that cancels.
Ah, yeah. Okay. Okay. Good. Thank you.
Okay. So what I have then for the second part, so I have this second C transform of psi is less than or equal to the minus the first C transform of phi at x. Okay, again, so just be by choosing y is equal to x. Okay, and again, using the fact that c is the metric, so c of x is 0. Okay, so now I need the lower bound. So the lower bound, I can use part A. Okay, so in particular, I can replace this this phi of c by phi c of x minus c of x y. Then these two cancel, and I get minus psi of c of x. So actually, okay, this is true then for all psi. Okay, assuming that the c is a metric. Okay, so then we're left with part C. Okay, so if I have any f with literally constant less than or equal to 1, okay, well, f of x minus f of y is going to be, okay, well, just by definition, less than the Lipschitz constant times c of xy, okay, which is less than or equal to c of xy. Okay, so then this means now that, okay, so I guess actually really what I've shown is that f and minus f are in the constraint set, but of course the minus sign makes a difference. Okay, so that's the three things that I needed to show, and so I've done it. So we have the Kantorowicz-Rubinstein condition. Okay, so next on the list is the Knott-Smith optimality criteria. Okay, so this essentially, right, so we're going to now sort of, I guess, show conditions where the optimal transport plan takes the form of an optimal, is induced by an optimal transport map. So again, I have this set. Okay, so my cost function now is just going to be essentially x minus y squared. Okay, for convenience, put the half there just to make things a bit easier. I have my set psi tilde, okay, which is going to be a set of L1 functions on new and L1 functions on new, such that the product of them is greater than equal to unit product of x and y. So the case is kind of very similar to the C transform, except for the C transform, right, it would be you have like a less than or equal to, and then it would be sort of C of xy, but somehow I've gone back from the C transforms more towards like the convex conjugate. So this kind of relationship between this sort of psi tildes is something like, yeah, the tilde gives you, it should I guess be something like half of x squared minus psi tilde, and then instead of taking the convex conjugate of psi, right, you can take the take the convex conjugate of psi tilde or the C transform of the psi. But anyway, okay, so so first of all, I let pi dagger. This is going to be a minimizer of the Kantorowicz form of optimal transport, and I'm going to take a minimizer, okay, of J in. Okay, so I guess I've sort of skipped a step here where I should really say that these psi tildes. Okay, instead of having like the C transform, right, I can just replace this with the convex conjugate. Okay, but the point is going to be is that this set this function psi tilde is convex. Okay, and kind of and y is in the gradient of psi tilde. Yeah, psi tilde dagger over x, almost everywhere. So maybe I can again sketch this out. So what I have, okay, so my psi tilde is sort of convex. So simply say it looks something like this. And what this is saying is that the support of my minimizer pi dagger is going to be in the gradient of this function here. So this is my psi tilde right there. Okay, so if I take the gradient, so the gradient should be sort of increasing. So maybe it looks, I guess I've drawn it quadratically, so it looks square, but maybe it looks something like this. Right, so then the point now is that my pi dagger, right, the support of that is on the purple line.
Okay, so on the other hand, if we let
again let pi dagger be in the space of couplings between nu and nu. Okay, and we suppose there isn't, some L1 convex low semi-continuous function psi tilde. Okay, such that the support of my pi dagger is contained in the graph of the derivative of psi tilde. Okay, so this just means so now I can start off with my pi dagger, right? And I'm assuming that there is some function such that pi dagger lives in the on the graph of the gradient, right? So I'm now assuming that my pi dagger lives on this purple curve. Okay, if that's true, then pi dagger is a minimizer of the cantoric optimal transfer problem, and this function psi tilde, this is a minimizer of the dual form, right? So it's what the theorem, I guess, essentially is saying is that if I want to know if something is a minimizer, right, I just have to check whether or not I can find a convex function such that the support of the plan is contained in the graph of the function. Right, so I didn't have a proper proof for this. I just kind of wrote down some sort of reasoning. Right, so if we just think about what we expect kind of in one dimension. Right, so in one dimension, we expect some sort of monotonicity in the transport map. Right, so if you imagine, we have one measure sort of here, another measure sort of here. If we're going to move mass from this measure onto this measure, right, then we're going to move it so that it kind of preserves the ordering. So in particular, if I move mass from x, to t of x, then I move mass from y to t of y. If x is less than y, then t of x should be less than t of y. Right, it's going to be no sort of sort of crossing over. Right, okay, so if I think still everything is sort of in one dimension, right, but now, okay, I allow mass to be kind of split. Right, then we have this sort of, a very sort of similar monotonicity property, right? So here my gamma, right, is going to essentially be the support of my optimal transport mapping. Okay, and what this is going to say is that, okay, again, if my x1 is strictly less than my x2, then I'm not going to move mass from y1. Okay, mass isn't going to move from x1 further than y2. Right, if that sort of makes sense.
Can you repeat that?
So maybe I can try and just try again. So if I have, right, so my x and my y. So if I move mass, so I'm moving mass from x1, it's going to go to y1, and I'm moving mass from x2, and this is going to go to y2. Then all this the property here is saying is that I can't have this. So if I put a y1 here and y2 here, so if I move my mass from x1 up to y1 and from x2 to y2, essentially this is not going to be optimal. It's always going to be better to move mass from x1. It would be better to kind of do it kind of this way around. This is all I'm trying to sort of say. But I write this down as kind of in this sort of way to try and make it look like this sort of cyclical monotonicity property. Right, so in okay, so in d dimensions, right, if I take a set of points xi and yi, okay, that are all kind of in the support of my optimal transport map, right, then what I expect is that any permutation of these points is going to increase the cost. Right, so if I'm mapping from xi to yi, okay, should be giving me a smaller cost than if I'm mapping from xi to any permutation of y. Right, and so okay, so now if you sort of know some sort of convex analysis, right, this sort of cyclical monotonicity property It's kind of exactly what you expect from the derivatives of convex functions. Okay. So I've slightly forgotten where these slides are going, which is probably indicates that maybe we should go for a break as soon as I can look over what the rest of the talk is contains. Okay, so if we're in sort of one dimension and we have sort of 2 points, right, then this sort of cyclical monotonicity property, right, is exactly this. Right, so if you write out all these sort of squares, you do the right sort of cancellation, what you have is that x2 minus x1 times y2 minus 1 has to be greater than or equal to 0, right? Which makes perfect sense, right? So I mean, either x2 and y2 have to be the biggest ones, or x1 and y1 have to be the biggest ones. Okay, and so now this is kind of where the convex analysis comes in. That the graph of the subdifferential of a function is cyclically monotone if and only if the function is convex. Okay, so this is kind of where we expect the sort of connections with between sort of our optimal transport, well, the support of our optimal transport plans, okay, and convex functions. So maybe yeah. So maybe I'll go through this slide and then maybe it's time for a rest. Okay, so this is Brennier's theorem. So again, it's in the same sort of setting as the not optimality criteria. So we use the same sort of cost, so this quadratic cost, and we need to not give mass to small sets. Okay, then we have the following sort of statements. So the first thing is that we have that there's a unique solution to the Kantorovich optimal transport problem. Okay, so this is something we we had existence before. Okay, and now the only sort of strength of this is to have uniqueness. Again, this is just sort of strict convexity. The second thing we have is that there exists an L1 convex lower semi-continuous function, phi tilde, such that pi dagger is just the identity across the derivative of phi tilde dagger, raising the measure mu. So again, this is kind of just the Not-Smith optimality criteria from a couple of slides ago. We also have that this phi tilde dagger and phi tilde dagger convex conjugate minimizes J. So again, this is just from the Not-Smith optimality criteria. Okay, so furthermore, if phi tilde is any convex function, okay, which satisfies this sort of conservation of mass property, then we have that the gradients have to be the same. So this sort of says that the minimizer of the sort of the dual form, right, is unique up to a constant. Okay, and then so finally then this gradient of phi dagger tilde. This is a solution to the Monge optimal transport problem. Again, this is probably not surprising because we had sort of very early on in the talk, right? We had this. I mean, this phi dagger tilde, right, was put this. This was equal to t, right? And we saw that if this was an optimal if this was a transport map, then this was a transport plan. So yeah, the optimality sort of carries through. Okay, so I think probably is a good point to stop here, and then should we half an hour, 20? What do you want to?
Yeah, so 20 minutes, 20 minutes. Yeah, sounds good. I don't think we have anything scheduled after the session, so there's flexibility.
Okay, so show me. I mean, I guess it's 25 to 3 now. So if we say 3 o'clock.
Yeah. If you want to go upstairs in the common room, we have coffee. Yeah. And for people that feel hungry, there is lunch over there. People who missed lunch. Is your lunch?
That's in the other way. Yeah, I will follow the ones.
What's the link to the phi tilde with the minimum formulation? How did that connect with the previous bit? So yes, a few slides before this.
Yeah, I guess I realised I didn't put this together.
Yeah, so how does this link with the previous formulation?
I could have done this. So I think from memory, what it kind of is. is you can either go through this like the C transform stuff or like the convex conjugate stuff.
Right.
And I think it's something like until the x is equal to half x squared minus phi.
Oh, I
X, something like that. So you can sort of when you do this like the C transform on the phi. So like yeah, so right, so it's like spin theme over y. Now you have half of x minus y squared minus pi x. Okay, something actually you like phi tilde here is theme. So they get what like half of y squared minus xy,
yeah.
and then yeah, minus phi x. Yeah, something is So of course, right. Oh, actually, right, because y, that's y there, so the y's cancelling it, yeah. The x there, the x plays no role, so it's, yeah, I'm out by a minus sign, I think, somewhere. Yeah, maybe that wasn't meant to be maybe that was meant to be a plus, that was a minus. But they just, yeah, it doesn't seem like that.
Okay, so you're saying right that this phi, the tilde here comes through a kind of transformation like this.
Yeah. And then it's so then essentially it's just rewriting the dual problem. Yeah, in terms of like the tildes, the tilde notation rather than the tilde notation.
So are you transporting one?
And the dagger, does that signify something else, or is the dagger just a marker somehow?
So I know you use the dagger when it's optimal. So
I see.
so I guess yes. So the reason is why I use like the dagger here is because I define it as being the minimizer here. At this point here, actually, I've not defined it to be. It's not defined to be the minimizer. But then it later turns out to be the minimizer, which is why I use it.
Right, I see.
1 over. Okay, fine. So they're just a
Okay, right. And so here the delta d's are the sub-differentials, right?
Yeah. Usually the same number of points at the beginning.
No, so this is just general.
And so this is saying the graph of
You're
the
starting
sub-differential.
Is if you want to estimate.
So is that assuming that it's
You actually know the
differential?
ratio.
So that's
No, because it's a common function. I think it's almost everywhere differentiable anyway, because it may not be. Yes, I mean, you could have.
it could be like x or something.
So, yeah, so if you're differentiating norm x, right, the exact the differential, right, would be, so it would be -1, +1, and then any point.
Oh, I see. So in this case, the graph is basically, you're basically kind of modulo the points where it's not a singleton. I see.
Yeah, so what you, so in this case, right, the claim would be the support of the optimal of pi, right, will be contained in this set here. So it could take. So this would kind of correspond to splitting mass.
Oh, I
We make it so
see. Okay.
So essentially, yeah, you're going to split mass wherever the function here.
In a way, we make it so
Yes, when where it's differential, right, then it's a differential, right, it's the second one point.
Right.
But then in general, it's not going to be, yeah, and then,
So you can have permutations.
and that actually, so that kind of, links you back to Brennier's theorem. What Brennier, so this is why you assume you don't give mass to small sets.
Oh, yes, I was going to ask, what are small sets exactly?
It's weird.
It's it just means that,
And
Because it
so.
corresponds to the order of interventions.
okay, as far as I'm concerned, a small set is just like a point. So all I mean is, the measure of any point. is equal to 0.
Okay.
An ordinary,
So this means exactly the set of points where we don't have
Right.
Yeah, where
distribution,
it's not function's not differentiable, right? Has measure 0 under mu, and then so we can kind of forget about all those.
the order.
And so this notion of a small set, does that have a precise definition where this is a special case, or you're defining it to be this?
I think so, if I remember, so a lot of this I learned from Villani, and I believe it's. I'm not sure there's like a really consistent notation like throughout the whole literature. So I think, if I remember correctly, I think Villani just sort of says, look, in our context, it just means that points have no mass.
Okay.
But I think he sort of, from my memory, we might say there's a bit of inconsistency how this is used. So I guess, it could be. You could end up getting something like fractal sets or something like this. Like how that? Okay. So but I mean, all we because you know that convex functions are Lipschitz, right? And Lipschitz functions are almost everywhere differentiable. Then you just essentially need that almost everywhere part to be almost everywhere.
Convex functions aren't necessarily limited.
I think they are on compact sets. It's locally Lipschitz, I think.
I believe that,
So you know that they're differentiable almost everywhere, but they're differentiable Lebesgue almost everywhere, and you just need Lebesgue almost everywhere to be mu almost everywhere.
Oh, I see.
So that's
okay.
that's why you need.
And so the optimal thing to do is
And going back even to some of your really early stuff, I mean, so the kind of underlying technical assumption throughout is that you have Polish spaces. And so, for example, in the early proofs, where I guess at some point you're implicitly using the fact that your space is Polish, right? But like even back to like the really early slides, like the first one, like the Monge formulation, is it basically you need minimal conditions essentially so the Prokhorov theorem is true, and then that relies on basically a Polish space?
I think so. I mean, like you might be able to get rid of some of these. Because I mean, like I can never quite remember exactly what all the conditions I guess for things like Prokhorov's theorem. But it's.
Sounds about right.
So it's basically a very constrained by variant
Okay, so originally,
saying if I fix this, how do I implement the other ones? And I implement the first one again, and you're kind of done already. So what you have, I think, is
some mass.
so add optimality.
And now I can change that, I can permute the whole.
I just say that.
Also, I'm Andy, by the way. I'm not sure we probably met.
No,
I guess we'll be future colleagues.
So are you okay? So I guess you're here.
Yeah, so I started as assistant professor here in January.
Okay, where were you before?
I was a postdoc at Bristol.
Okay, right.
Yeah, so I was on the cosines program, which is why I'm here.
Nice. So were you working with, is it Anthony Lee?
Yeah, and Christoph. And
If you fix it,
Right.
you have a specific.
I know that
You can do the same.
So you're starting in January?
Oh, no, I've just started, so been in the job for 4 months now.
Okay.
3 months.
How are you enjoying being here?
Yeah, it's been good. I mean, they chucked me in the deep end. I was teaching a full course, basically as soon as I started. I was moving house hopefully at the end of this month. So soon I'll feel much more stable. Because we're still kind of living in Bristol, so I was going back and forth during terms. It's been good. I mean, so Gareth Roberts was one of my PhD supervisors.
Okay,
I was based in Oxford, so I already knew a lot of people in the department. So it's quite nice. I wasn't starting from nothing, and I started the job.
If you fix the same.
And when is it you're starting yourself?
Starting in August.
August. Okay. So you have a bit of time before term and everything.
Yeah, it should be quite nice. I mean, because I did my PhD here, so I kind of already know the area a bit. So I left like in 2015, so just 8 years ago. So I knew the area, I guess, past this. It's nice to move over somewhere where I don't have to kind of worry too much about teaching and things like that.
And hopefully.
So who did you do your PhD with?
Did it with Florian Tile and Adam Johansson.
I don't know the first person.
He's in maths.
Okay.
More calculus of variations, materials.
Cool. And was your PhD in maths or was it in stats?
So I was in Masdoc, so I was kind of one of these
Okay.
between the two. But that's the probably was more in maths than I was in stats.
Okay.
Maybe I'm saying something. No. I mean, like, this is what I'm thinking.
And you'll be moving from Manchester, is that right?
Yeah.
Say you run something.
Are you in Manchester?
Yeah, currently, yeah.
Okay. I did my PhD in Manchester.
Oh, nice. Who did you do it with?
Simon Cotter and Thomas House.
Okay, right, yeah. Yeah, they're both, yeah, they're nice. These guys.
Yeah. Can I ask you 2 questions?
Yeah, of course, yeah.
Because me and Sam arrived late because of the trains and so on, so I feel like I
Yeah,
missed some.
nightmare.
I mean, because a bridge was 30 miles.
Seriously? Oh, that's bad. Okay.
Anyway,
That's what you're
so yeah.
So let's say it's a course C1. Yeah.
Can we sort of like go over the motivations a little bit of?
Yes.
Yeah.
So.
Can we follow what?
Yeah, I mean, I can.
Hopefully, it would.
Yeah, I can give you like a very 5 minutes to try and get you up to.
Okay, sure.
So I can. Oh,
Because I was talking about it with Sam, but then I have further questions, and I feel like I will ask them to you. So basically,
Okay, gotcha. Right.
in simplification, right, we want to minimize the cost of
change, so we should that
X to Y essentially over the couple of measures, right?
Yeah.
Okay, fantastic. Alpha and
You
beta.
can, if you write the permitted version of this plan into the objective.
Generally speaking, I think you was like. So from here to here, maybe you consider functions, right? Rather than just generic joint cost functions, maybe it's like I don't know, a cost function F plus a cost function G. Does that make sense? Such that it's not joint anymore?
Yes, this I guess it's a dual form, yeah. So I guess.
Yeah, we're getting to the dual form, yeah. Exactly. So the step from here to here is just saying, forget about the joint cost and then only consider like single variable functions. Is that the step?
Yes, I think what you've written down there is exactly the dual form. I think I was using this course.
Yeah.
So here. Y1. Yeah.
Or we can just forget about this and I can like let you.
Yeah, I guess, yeah, I can, yeah, just go through what I covered. So I guess if I start off like the motivations, talking about,
What do we have with the?
cutting distances.
Yeah, this flats out and we don't want that, right? Because if you forget, it doesn't represent what we want.
Exactly, yeah, so then, transport
Doesn't,
distances. Okay, so then one for, okay, okay, so we know that, like this.
Okay.
Example, transport map. Okay, then so I mentioned, the cases, P versus distance. Transport maps don't always.
But also one random question here, if you go back one. Why do you include just, it's just about, yeah, I guess it's just about X, there's no,
And then.
I mean, why is the X? That's why probably you integrate with respect to just mu and not.
The cost is.
You also because you set the constraint, and so whatever happens to mu happens to nu somehow. Okay.
Yeah, exactly, yeah.
I mean, this is the kind of deterministic formulation where if you're at X, you must be set to T.
No, C2 is up here.
Yeah,
Split, yeah.
X1.
Gotcha.
Which is why this is a problem.
Yeah, exactly, yeah, so this, so then you can't split mass, so the contorted form essentially is the relaxation of the Monge form is now.
I was assuming that you had a
mass from,
method.
1.7 points.
Sort of.
Oh, yeah.
Type.
This is where we went from maps to plans.
Is it variant?
So I always hesitate before I say it, because I can never know which one's the map, which one's the plan. Because T is always the map, right? So pi is the plan.
Okay, pi is the plan. So I think the map
If
then
I had
is
to
mass.
design one of these algorithms, this would be.
So-
What's the plan?
So plan,
Okay.
the plan is a measure on the coupled space. So a plan allows you to split mass. So
Okay.
So essentially, pi of xy sends mass from x to y. This is in context to the map kt, which sends all the mass from x to t of x. So the problem being that you can't send mass from one point to many places in the one form.
Gotcha.
I mean, as someone who comes to this from stochastic processes, I just think of pi as a kernel. I mean,
That's not.
do you see what I mean? It's the same information, right? It's saying for each x you have a measure.
Yeah.
And I suppose, okay, kernel has some extra measurability assumptions, but at least, yeah, that's why.
Yeah, I guess you can.
Did you see what I mean? As
Sorry, I
in,
wasn't
you can,
listening.
you can also think of pi as like a
I
mark,
guess
it's a
it's
kernel. That says for every x,
it's
it's a probability measure on y.
Gotcha.
But I guess it's more, it also goes the other way, right? So it's,
Yeah, because it won't quite be like that because you had to kind of normalize it. So you get a kernel is pi of xy divided by mu of x.
yeah.
Okay.
And the reverse has to be true as well, that if you fix y.
I mean, I don't know anything.
No, it's just a measure of the joint space. Okay, so it's slightly more
Intuitively,
general, no, specialized.
your plans would be.
Okay. Yeah, I started missing things at this point because I did not understand that
Your
pi was a
line,
plan, we could split mass.
This one's x1,
Okay.
this one's x2, and this one's x3.
But no, but there always exists a kernel, right? As you
Yeah,
can always
that's
write pi
Y,
dx dy
two.
as some pi sum x dx, and then some p x dy, right? As in the existence of such things
That's this map.
is guaranteed.
So if I was running an algorithm. and I
As in,
didn't know
okay, in this case, I guess
anything
this would
about
actually
it,
be
then
mu, right? This would be mu
notification I give
x.
it gives it-
Yeah.
might change what
And
comes
there
out.
is a kernel that
I guess would
exists
be
with the right
first
margin
condition I would try is I would.
to make
okay, which
this
is the
true.
closest, which.
Yeah, I think like some disintegration measure, right?
Yeah,
Well,
exactly.
what's the closest x, right? Something that respects this order.
Yeah, no, yeah, I agree.
Like I would feed in x1,
Okay.
x2, x3.
Okay, so
Y1,
I kind of made a case for
Y2.
linear
So
programming.
that pi, is it
Instead of
still the
trying to
plan?
Feed in x3.
So,
x2, x1.
Yes, okay, yeah, so pi is always a plan.
Because in this
But
case,
actually,
you-
here I'm
it
going
has to
to
spin
argue
out
that
the
actually you can think of it just as being a matrix. Because so I did, we just discretize everything.
This is like.
Yeah, so if we discretize everything, okay, then we have parts at point x and yj. Then my pi, I can just think of this now as how much mass do I send from xi to yj, and so I index everything, and so I end up with a n by n matrix, you know, with restrictions on the column sums and the row sums.
Feed the data
Yeah, and
in
then
so that
so-
the solution looks.
What I end up with this problem here is I think this problem here, where this is a linear problem, right? So this is just a sum over all ij, cij times pi ij, so a linear string, and then this is a convex set. So this is a linear program.
So pi here is a matrix. What is pi on the right? Pi is a vector or a matrix?
I think it's just a matrix, yeah.
Okay,
So
so
this,
matrix multiplication.
this dot here is essentially, you know, I'm vectorizing, so I mean, I'm really.
Oh, I see, right, it's not matrix multiplication, it's actually, what would you call it? Like a Frobenius sum or something.
Yeah, it's probably the, yeah. For me,
Frobenius
it's in a product or something like that, I guess.
Yeah,
maybe,
I guess you would.
So C is a matrix, pi is a matrix.
Yeah, and you're summing coordinate or coordinate like that, so it's not actually matrix multiplication.
Yeah, I mean, I guess I put the dot in because it's like a
Yeah.
dot product,
Yeah.
but
Okay.
We're in N2K lab.
But that's the Cantor-rich formulation, no?
yes, yeah.
Then if you discretize everything, that's the formulation, right?
Yeah.
Oh, this sum.
So that's the point is right. It's just it's a linear program. It's so Cantor is kind of like one of the founders of linear programming, like for this reason.
This week.
Cost x, y, t, 6 squares, and then
I don't, in my,
and c.
I don't know, maybe I'm just getting a bit confused, but in my head,
Okay.
I tend to think of.
Gotcha,
plan
okay.
as
how you rearrange.
Okay, yeah, so here I just wanted to kind of argue that if you give me a transform map, right, that induces a transform plan. Okay, and just for some reason, that transform map tells you where to move, x, mass has to move all the way to t of x, so you just design the plan which does exactly the same thing. The point is the plans are more restrictive than the maps here, so.
The plan is more restricted than the map.
No, sorry, the other way around. The
okay.
map is more restrictive because the map
Okay.
says here.
Am I right?
Yeah, so if T is a transport map, then you can define a plan as just being.
The identity goes with T.
Yeah.
Oh, as in it doesn't change X, but it changes Y.
Yeah, so this will be the set 5. This will be this set of mu such that x is in A and
I think probably what will happen will be at the end of the workshop. So
T of x is in B.
they won't be sort of full problem.
Okay.
So it's the amount of mass, I guess, which is getting sent from A to B.
Okay. The amount of mass is good.
Yeah, and so you can, when you want to kind of check, okay, that,
So I'm going to write that down. A plus B.
so this is using this definition here, actually. I've assumed that this.
Okay. Okay.
Yeah, again, in that guess proper mistake, yeah, it should be the.
Oh, and that's why you were saying that the munch is like an upper bound for the current average.
Yeah, exactly. Yeah. Yeah, because every map induces a plan, right? Then essentially, yeah, for every t here, we have a given pi here, the same cost. Then of course I have potentially a lot more plans here because my t induces a map, but not necessarily the way around. So yeah, so I get kind of this inequality here, kind of trivially.
Okay.
So then yes, then towards the end, what I said before is kind of when we have an inequality. Okay, so it kind of turns out if my map can be, so if my plan can be written in the form of a map, then the equality actually holds as well, and the margin and the cantoric forms are the same.
Can you repeat that sentence?
Yeah.
So if I assume that my optimal transport plan takes this form here, so it is induced by a map T, then pi being optimal would imply that T is also optimal in the modern sense. Yeah, so then I had like proposition on the existence of solutions to the cantoric problem, which is just a straightforward sort of compactness plus lowest any continuity.
Yeah. And then I wanted to ask you about the C, CC, tilde, and dagger.
Yeah, okay, so so we have duality, which we kind of wrote in this form here. And so where the C transforms, okay.
So, phi is a solution. It's like a phi C, sorry.
So phi C. So here the capital phi is a set. So essentially it's the set of functions which are sort of L1 with respect to mu, L to nu, and such as here. Yeah, and then J is the sum. Okay, this is kind of our dual energy. Right, and the point now is that the cantoric optimal transfer problem is given this sort of has this sort of dual form here, where it is the supreme of phi C.
Okay. You could call it residual energy.
No, I didn't. I think I called it dual energy.
Dual energy, okay.
But I don't think I've ever called it that before. I just.
Okay. Why would you care about the J?
It turns so actually this. It's just a very useful form actually. Kind of like a lot of proofs kind of use this dual form. Or it also gets. I mean, duality gets its useful anyway in terms of sort of numerics. So these are the dual optimization algorithms. It also comes in. So these. So I have like the Kantorowicz-Rubinstein formulation here. This is basically one can sort of manipulate the other dual forms, right? Right. This dual problem here, and this is what gets used in like Wasserstein-Ganz.
Okay. And tilde and dagger? I mean, I suppose the CNCC are essentially. Things you have to apply, just solutions you have to apply to get here, I suppose.
So I tend to just use dagger actually to kind of indicate optimality. So I sort of made it. Yeah. So where did the? So I kind of realized I made. This is the problem, I guess. Okay, so this was a new talk, and I realized I probably need at least one more slide before this, really. So the dagger just means that this is optimal.
So pi dagger is a.
So it's just a point that I can.
Pi dagger, is it a plan?
Yes, it's a plan, right? So it's in this set. Here, yeah, and then minimize it.
And then you have pi. I don't remember what the star meant.
So the star is the convex conjugate. So this is
the convex conjugate or pi tilde dagger.
Yeah. So the dagger just essentially means fixed.
Okay.
Yeah, and so I use tilde because we have. Yeah, essentially there's a change in notation, and I didn't sort of go through this.
Okay.
So before, actually, so my dual form is given in terms of phi and the psi, and in terms of like C transforms. There's a way to put this back and to.
So I think they use the
Okay, people, can you actually write in the chat that we are starting?
Know how to do that?
Yeah, there.
Not here.
No.
Sebastiano, you do it.
Good. Okay, yeah. So here.
This one, okay.
What is it?
That's a long one.
What are you doing?
Yeah. I think actually that's everything that I've said.
Okay.
I think that's I noticed it before.
Ah, wow. Well, I guess it's fine without maybe here chat. Yeah, you just write. We are starting now with the second part.
Starting now.
Yeah. Switch screen.
To
Yeah, that one. Perfect. Yeah, full screen.
right.
All right. Yeah, you can start.
Okay, thanks. Okay, so guys, welcome back everyone. I hope everyone's refreshed. Okay, I would say we've got over the hump now. I guess the next three sections. So a little bit of work to do, but then okay, then it starts getting a bit lighter as we sort of wind down to Monday afternoon. Okay, so for metric properties, the first thing I just wanted to say is, and maybe this is not a connection that gets made too often, but actually it's quite an easy connection to make, is that you can actually write total variation in terms of an optimal transport framework. So I guess when I said metric properties, most of you probably thought I was going to go straight into the Wasserstein distance. now we'll have one slide of variation. Okay, so if we just define variation, okay, in the normal way, so the largest value over set A of mu of A. Right, and the theorem is that actually this can be written, so the TV norm between mu and nu can be written as an optimal transport problem where the cost is the binary valued. So C of xy is going to be equal to 1 if x is not equal to y, and it's going to be equal to 0 if x equals to y. Okay, and the proof is kind of like a nice sort of application of Cantor-Rich-Rubinstein duality. So if you start off with the with the optimal transport problem, okay, Cantor-Rich-Rubinstein duality just tells that this is the supremum over f of integrals integrating with respect to mu minus nu, and this supremum here will be taken over all f that are one Lipschitz continuous, and the set of functions that are one Lipschitz continuous are just going to be okay, so the cost function here is either 1 or 0, right? So actually this is just going to be the supremum over all functions f which go into 0 or 1. Okay, and so if you get the supremum here, right, this is just exactly the positive part of sort of mu minus nu, right, which is the TV. No.
Didn't CAT so lower semi?
So what? Sorry.
The cost function, does it increase lower semi?
That's a good question. Okay, so I guess I should double. I think it is lower semi-continuous, right?
But I just don't have to do it.
Yeah, so I guess like lower semi-continuity. So the cost function, I guess, looks essentially like that, but then takes that point there. But there, so lower semi-continuity would just mean that any sequence. So what do you have? So I need like limit as n goes to infinity of c. So I guess like let's say it has to be low semi-continuous in each argument. It would have to be greater or equal to c of x y. Okay, well yn is converted to y. So yeah, but okay, but good point. I hadn't. Yeah, I thought I might have missed something there. Okay, so this is it's sort of like just a casual sort of throwaway mark that indicates TV comes out as rewritten as an optimal transport distance. Okay, but of course, like the more common sort of when I say so, we'll do sort of look at the metrics properties. Wasserstein sort of cases is the kind of the more usual thing to talk about. Okay, so if we P subscript P is going to be a set of probability measures on X with bounded P to norm. Okay, and define the Wasserstein distance as just being the pth root of the optimal transport problem, where the cost is x minus y to the power of P. Okay, so my first comment is that the Wasserstein distance is finite on the set of probability measures bounded P to moment. Okay, and this is kind of very easy to show just because we can bound sort of x minus y to the P by x to the P plus y to the P, with the constant P. Okay, so then of course, right, we're bounded by. I'm making a note of all my typos so I can correct these. So this second integral here, of course, shouldn't be there. I can't see what slide we're on. Okay, so then I guess the more important theorem is to show this is a metric. Okay, so we have several things to check. So first of all, is it positive? Okay, yes, this is kind of clear. Symmetry, okay, this is also clear, and this is just follows from if I if I take any plan pi in the sort of right coupling space, if I define S to be my sort of the kind of symmetry operator, so S of x y is equal to y of x, so it just switches the x's and y variables around. Okay, then the push forward of pi by S is just the marginal, so just switched around. Okay, which kind of makes complete sense. Okay, so then symmetry then follows straightforward. Okay, if the Wasserstein distance is equal to 0, okay, this then means that the support of the optimal transport plan has to be contained in this set XX. Okay, just along this identity mapping. Okay, so this then would mean that mu has to be equal to nu. And of course, if the Wasserstein distance between mu and mu being to 0, this is also. So then, okay, all the way kind of left is to do the triangle inequality. Okay, so this is almost the same as the normal sort of LP sort of triangle inequality, except we kind of have one more sort of step, and this requires this sort of gluing lemma. So this says that if we take 3 measures, so 3 probability measures in RD, we take 2 couplings, so we have pi of xy is the coupling between sort of mu and nu, and pi of yz, the coupling between nu and omega. Then there exists some gamma on the sort of 3 times product space, such that if I project into the first 2 marginals, I get pi of xy. If I project onto the second and third marginal, I get pi of yz. Right, so this now just allows me to sort of build everything. I don't know if I go into. I think I might in the next slide go into a few details. Okay, so mu, nu, and omega. These are all probability measures. Okay, I take my pi of xy, pi of yz. I assume they're optimal for the Wasserstein distance between mu and nu and omega. Okay, then I take my gamma. Okay, which has the right sort of first 2 marginals and the right second and third marginals. And then okay, I can use this now to define a potential map between the first and the third, just by taking the first and the third marginal of my gamma. Right. Okay, so it's very easy to show that this has the right sort of marginals. Okay, so this push forward of pi of xz onto its first marginal is mu, onto its is how you want to number them. If it's second marginal or third marginal, it should be omega. Okay, so then this is kind of an admissible. Yeah, it's in the right space. Okay, so the Wasserstein distance now between mu and omega, that's going to be bounded by this candidate plan here. Okay, so now I can sort of write this as being sort of an integral over respect to gamma over the sort of triple product space. I can use my normal sort of LP triangle inequality here to write this as the half against my x minus y, my y minus z. And then okay, so here I notice there's no z dependence, so I can take out the third marginal. Here I can take out the first marginal. Okay, so I end up with just integrating respect to pi of xy and pi of yz. Of course, I chose these so that they're optimal. So I end up with the Wasserstein distance. Okay, another typo. There's no equality. Last line. Right. Okay, so the next proposition is that these, okay, on bounded spaces, at least all these Wasserstein distances are essentially the same.
Can you go back on slide 1 second?
Yeah.
Would that be like, or like, what was the other one? Yeah, superimposable integrals, or like, especially at the end.
So
to be the Wasserstein distance, so am I missing something?
It's because here I chose it, so if I go back one more slide.
No, it's already.
Yeah, so I chose it so that it's already.
Okay. Okay.
Yeah, I could also do the same thing, right? With, I mean, I know that there's a minimizer, so I can assume it, but I could also just do this with like an almost optimal plan as well if I didn't know that there was this minimizer, and yeah, same idea would go through. Okay, so this proposition basically says that at least if x is bounded, all these Wasserstein distances are essentially kind of the same. So I always kind of have this sort of trivial lower bound between the one Wasserstein distance and the p Wasserstein distance. And if my space x is bounded, then I can sort of get an upper bound on the p Wasserstein distance in terms of the one Wasserstein distance as well. And I think, yes, the proof is the first one is just Jensen's inequality. And then the second one is kind of even more trivial. I can just say, well, x minus y to the power of p is just less than or equal to the diameter of x to the power of p minus 1 times x minus y, because this is as big as x minus y can possibly be. Right, so yeah, I
This is sort of nice. It means I don't really have to worry too much about what my choice of P is. I can just do everything with whatever P is most convenient. Okay, so
Sorry, just a bit better. What is the diameter of X?
oh, I guess meaning like the largest possible distance between X and Y in the set.
Oh, right.
So I think it was this diameter because I guess I think it would just be if it's a circle, right? Then it is the diameter.
Okay, yeah.
Yeah, I guess or the smallest ball that contains the set.
Yeah.
Okay, so this I guess is one of the sort of most well-known facts about Wasserstein distances is that they metricize the weak star convergence. Okay, well at least when X is compact. Okay, so if X is compact, I have a sequence mu n and some mu in space of probability measures. Then I claim that mu n is converging weak star to mu if and only if it's converging in the Wasserstein distance. And yeah, that is a mu n there, and that should be a mu. Okay, a lot of these slides were kind of old slides. Some of these slides are new slides, and you can see which ones are the new slides and which ones are the old slides based on the number of typos. But I tend to put these on my webpage, so in case people want them afterwards, right, so you can get the correct version. Okay, so I've sort of written down the proof. I think it's probably end up being some more of a sketch proof than a full proof. So the first thing is we only have to consider the case when P equals 1, right? Because the past, we can upbound and lower bound, and the P Wasserstein distance by the 1 Wasserstein distance. So, let's just let P be 1. Okay, so to start off with, let's assume that the mu n converges to 0 in the 1 Wasserstein distance, and we let f be any sort of Lipschitz function. Okay, so what we're going to want to show, right, is that the integral of f d mu n is converging to the integral of f d mu. Okay, so if f is Lipschitz, right, then while f tilde being f divided by the Lipschitz constant of f, this is going to be 1 Lipschitz. Okay, so now we can sort of bring in as, we can apply our sort of Kantorowicz-Rubinstein duality theorem. Right, and we're going to know that, okay, 1 over the Lipschitz constant of f times f, this is just the integral with respect to f tilde. Okay, and then this is bounded by the 1 Wasserstein distance because this is a candidate in the admissible set for the Kantorowicz-Rubinstein theorem. Okay, so we know then that this is converging to 0. Right, okay, and I'm not sure why. Okay, so yeah, so this is an upper bound, right? I can do kind of the same, the lower bound in the same way, and I can conclude that then that that I have this convergence to 0 here. So of course, right, I now know that mu n is converging to mu weak star. Right. Okay. Okay. So on the other way, I assume now that mu n is converging weak star to mu, and I let fn be a 1 Lipschitz function, okay, which is satisfying this sort of inequality here. Okay, so I know this. So again, this is the Kantorowicz-Rubinstein theorem, right? So I know that. So all I've not wanted to assume that there exists some fn which achieves the maximum in the Rubinstein-Kantorowicz formulation. So okay, so if it does, right, then I could just choose fn being equal to that to maximize it. So instead, I've just chosen one that's kind of arbitrarily close to the maximum, right? And I've assumed that I'm within sort of 1 over n. So no sort of problems there. Right. Okay. Now I let my fn tilde be fn of x minus fn of x naught for some x naught that I can just fix. So I just pick any x naught, right? So I'm just sort of shifting it. So this is just, it's a constant with respect to x. Of course, depends on n. Okay, but I do it like this so that I now know that these fn tildes are equicontinuous and bounded. Right, so this essentially follows from the fact that these fn tildes, they all take the value 0 at x naught, right? And they're all sort of 1 Lipschitz functions. Okay, so I can apply Arzello-Ascoli, say that it exists a subsequence such that fn tilde is converging to f uniformly. Okay, and now I just kind of have to go through the sort of algebra to make everything work. Okay, so I have the lim sub of the Wasserstein distance. This is, by
integer by choice, or my fn tilde, because of course by adding a constant here makes a difference here, so I can have my fn tilde here. Now I can divide this into two parts, so I divide this with an L infinity term on the difference between fn tilde and sub f, okay, which is my limit on my fn's. Okay, and then I have what's left over. So here, right, I know that this is converging uniformly, and here, well, I've assumed that mu n is converging weak star to mu, and this is for an f now that's fixed. So this term here is going to 0, this term here is going to 0, so everything's going to 0, so I'm done. So.
Need to use compactness.
Compactness, it's used here, because I guess it's not going to be bounded. So yeah, so going from showing that these fn tildes being Lipschitz to being bounded, yeah, I need a compactness.
In general, like, you get the other direction that you use compactness.
Yes, you're right. So I actually thought I wrote it down, but I haven't. So if you take away compactness from here, what you have is that weak star convergence is equivalent to. Sorry, I think it's weak star convergence plus convergence of peak moments is equivalent to Wasserstein convergence. Yeah, but in compactness, yeah, you don't have to worry about the convergence of peak moments.
When you remove the compactness condition, you have convergence and then Wasserstein implies convergence in weak star.
Yes, I think that's right. Yeah. So so if you have convergence in Wasserstein, yeah, they converge. It implies convergence, yeah, weak star, and it also implies convergence of peak moments. Okay, so the next thing I'm going to talk about is kind of well, I guess it depends how you count these things. Either the third formulation of optimal transport, or if you count duality, I guess it's the fourth formulation of optimal transport. This is in terms of like the Benamou-Brenier fluid dynamics formulation. Okay, so this is kind of like a very different way of thinking about things, but actually it kind of leads us on to geodesics and this sort of thing. Okay, so we think of a probability measure mu now as being the initial state of some fluid, and our probability measure nu is going to be some desired final state. Okay, so what we want to now is think of the Wasserstein distance, okay, particularly the two Wasserstein distance. This is going to be the minimum amount of kinetic energy required to deform the first probability measure into the second probability measure whilst preserving mass. Okay, so to kind of make this a little bit sort of more precise, I'm going to consider this so this row here is going to be, in its first coordinate, it's going to be time, in its second coordinate, it's going to be space. So at time 0, rho is going to be mu, so the initial state. At time t equals 1, rho is going to be nu, okay, which is going to be the final state. Okay, and then sort of in between, right, we're going to have a rho t, and this is going to follow some vector field given by v of t. So this is kind of my velocity field. Okay, so the kinetic energy is up to a factor of 1/2. Mass times velocity squared, right? So my mass is given by my rho, thinking this is like a density, my v, okay, my v squared here. So I integrate now over all time and over all space. This is kind of the total amount of kinetic energy, which is going to be required to deform rho from mu onto nu. Right, okay, so what it kind of turns out is that the Wasserstein distance can be written as the minimum of the kinetic energy over all mass preserving flows. Okay, so the mass preserving flows, okay, this just means that my rho and my v have to satisfy the continuity equation, which it looks like I didn't write it down unless it's on the next slide. No, I didn't. Okay, I think this is like slide 60 or something, so I mean I was getting tired as I was adding these slides. Okay, so so this sort of, so that mass preserving means that mass isn't being created or destroyed, so that implies everything kind of has to be transported, right? Okay, and then it's perhaps, at least I think initially this is maybe quite sort of surprising that is sort of the kinetic energy. This sort of relates to the 2 Wasserstein distance. But again, we can think of this in such a way that maybe it's not so unnatural. So if you think now as okay, so we move mass from x to t of x, and let's say we move in time 1, right? It sort of makes sense that we'd expect this mass to be moved in constant speed, right? So the speed at which we're going to move at then is just going to be t of x minus x divided by the amount of time, right? The amount of time is 1, so this means the velocity is going to be t of x minus x. Well, this is exactly our cost function, okay? But this is saying our velocity, okay, is just t of x minus x. So if I just substitute in v of t of x is equal to t of x minus x, right, then I get back the Monge formulation here. Okay, so there's some sort of technicalities, right? I kind of had to argue that okay, that the time dependence isn't there, and so I can kind of reduce this down to sort of a time t equals 0 integral, but one can kind of do all that, okay, and this then kind of links why we kind of expect the kinetic energy and the Monge form to coincide. Actually, that's kind of all I said here, but okay, but it does lead on to geodesics. Okay, so I'm not sure if anyone's sort of done very much fluid dynamics. I mean, I haven't done a lot, so I know really very little about fluid dynamics, but I do know, I guess, like the sort of Lagrangian and Eulerian perspective. So the Lagrangian perspective is you kind of follow one particle around. So if you look at sort of kind of how one particle moves, so again, if I have my mu and my nu. So I pick a particle here, x. This gets sent, say, up here to t of x, right, and I just follow the path of this particle. Right, and this guy is going to move at a constant speed. Now he'll start off here, time t equals 0, time t equals half. He'll be here, and time t equals 1. He'll be here, and from his point of view, he's moving at constant speed, right? Right. Okay. So if x to t of x is the optimal map, right, then we can just we essentially define, as I kind of drawn here, this sort of this interpolation between x and t of x. So at time t equals 0, right? So when this is t is equal to 0, right, this disappears, and then just get t0 of x is equal to x, and t equals 1, right, I get t of 1x is equal to capital T of x. So I'm just moving between x and t of x in a straight line. Okay, so the speed of this particle, so I guess actually this is slightly what I said on the previous slide. So the speed of this particle is just going to be t of x minus x, okay, so distance over time. Okay, and this actually gives us a way of sort of interpolating between two measures. Right, so if I do this for every single sort of point here, so then what I will sort of have is that at time t equals half, right, I have sort of all my points are going to be here. So this measure in between the two is exactly going to be mu, which has been pushed forward by the maps of t a half. Right, so this kind of, so if we let sort of rho just be mu pushed forward by t evaluated at time t, right, then this gives us a way of sort of interpreting between two measures, and this will turn out to be kind of like the geodesic in a formal sense. Right, okay, so the first thing we can notice is that rho 0 is mu and rho 1 is equal to nu. Okay, so I guess I didn't sort of assume very much about sort of geodesics. So as far as you're concerned, right, all we need to kind of know is that the geodesic is essentially a straight line between 2 points. Okay, so okay, so it kind of means exactly sort of exactly this, right? So the triangle inequality, right, will always tell us that this is less or equal to these 2 points here. But okay, but the fact that we have an equality here means that this rho of t has to kind of exactly be on the line between mu and nu. Right, so when this sort of happens, okay, we can sort of say that rho is going to be the geodesic. Okay, and yeah, the initial velocity of each particle, right, this is exactly equal to just the difference between the transport map and the density. So v of x is equal to t minus x. Okay, and what this means is that I can sort of write the Wasserstein distance as being the L2 norm of the initial velocity with respect to mu. Okay, so now I guess this sort of, you know, if you sort of have a sort of a background or a notion of sort of Riemannian geometry, you might sort of think, okay, this is quite interesting because now this is like, you know, there's now not just sort of inner product on this space, and I can sort of I can think now as v of 0 as being the tangent vector. Right, so yeah, so this is kind of what people mean when they say that the Wasserstein space has like a formal Riemannian structure. It's because we can kind of define these sort of these tangent vectors. So v, so here I have the distance between sort of mu and nu. This is equal to, you know, essentially the L2 norm of the tangent vector, okay, which is by v. Okay, so I just have some pictures here, I guess, of kind of what's interpolating, you know, with GD6 in the Wasserstein space compared to GD6 in Euclidean space. So if I start off at the top, maybe in the Euclidean space, so here we have like a tall, thin Gaussian, here we have a short, fat Gaussian. So when I do my interpolation, the tall, thin one becomes a bit shorter, and my sort of short, fat one becomes, you know, starts to grow. And so one's kind of being destroyed, one's being created, and this is kind of what the interpolation in Euclidean space looks like. On the other hand, in the Wasserstein space, right, then we have it behaves differently. So the tall, thin Gaussian, it starts becoming a little bit shorter, a little bit fatter, and it moves. Okay, and so eventually it moves onto the short, fat Gaussian. Okay, which we want to. The same thing kind of happens in 2D, right? So if I start off with, you know, Gaussian in the bottom left-hand corner and one in the top right-hand corner, right? The interpolation, the Wasserstein space, is just the Gaussian being sort of shifted across, whereas in the Euclidean space, it's kind of one Gaussian being destroyed and the other Gaussian being created. And this, I guess, is sort of maybe nicer in terms of sort of images here. So we have, you know, an image of two sort of people. And the idea being in the Wasserstein space is we should kind of see these sort of features sort of moving around, kind of, you know, so the eyes move a little bit, you know, the nose moves a little bit. Whereas in the Euclidean space, you kind of see a lot of, you know, sort of blurring around where, you know, the new set of eyes are sort of growing behind the old set of eyes, and this maybe isn't sort of as physically natural. Right, okay, so I have like a few sort of special cases. So the first thing is like in one dimension, everything kind of is much easier. So in 1D, essentially it's a sorting problem. So if you imagine now your sort of measure is just, you know, sort of buckets of sand, and you just want to transfer these buckets, you know, from one row to another row, right? Then you just start at one row, right? You know, you pick up your first bucket, you go over to the second row, and you just empty the bucket, and you go back, and you just do that until your buckets are kind of all filled up. There's not really any sort of optimization. So actually, this can kind of be sort of expressed quite nicely in terms of the cumulative distribution functions. It's a case if I let f and g be my sort of CDFs. Okay, so I'm going to work with, you know, with the inverses. Okay, I think probably I'm just going to assume that these, you know, that f and g are actually invertible to make things kind of easier. But in general, you know, they don't have to be invertible. So okay, so f inverse. Just think of this as being literally the inverse of f. Okay, so then the following theorem is that if a cost function is given, you know, some convex function of the difference between x and y, then we have that the optimal sort of transport map has this CDF here, which is just given by the minimum of fx and g of y. Right, so what this is saying is that, you know, if I think of right, so I have one measure here, one measure here. So using this on my buckets of sand. And I want to know how much mass is kind of contained in this region here. Right, so this will be the, so this is my point here, x, this is my point here, y. And then the integral over here would be h of xy. Okay, well, I just look at the smallest amounts of mass, you know, that's in these 3 buckets here, and it's in these, let's say 4 buckets here, right? Okay, so the point is, if I define my pi star like this, okay, then okay, so I can check that it has the right marginals, okay, but moreover, it's an optimal transport plan between mu and nu. Right, and then okay, it's just it's just kind of a little bit of algebra to show that actually the optimal transport costs can be written as the difference between the sort of the inverse CDFs. I think this even simplifies on the next slide. Yeah, exactly. Yeah. So if the cost function is just equal to the difference between x and y, then the optimal transport cost is just the L1 difference between the cumulative distribution functions. And this is kind of supposed to be sort of represented here. If I have my measure sort of mu here and my measure nu here, so if I plot the CDFs, right, the optimal transport cost is just the area of this sort of yellow curve here. Okay, so this kind of gives rise to what people call slice Wasserstein distances. So I hope these numbers here are correct. I'm not a numerical expert. There's probably people here which know more about the numerics than I do, so maybe someone can correct me if I'm wrong. But essentially, I think so. Linear programming, you know, is the cubic order, option algorithm. I think so. That's squared order. So the synchrone algorithm. This is kind of state of the art. This is in theory, I guess, sort of essentially linear. So I think someone will probably end up talking to you about the synchrone algorithm later this week. This doesn't solve the optimal transport problem. It solves an entropy regularized version of the optimal transport problem. And so this of course means you're solving an approximation. Essentially, the worse the approximation, the better the numerics. So this order here contains a constant which depends on the entropy, and so this constant here gets smaller as you put in sort of less of the entropy. So the constant gets bigger, the less entropy you use, which means the more accurate you get. So essentially you have a trade-off between accuracy and computation time. But anyway, so in 1D, you're essentially just solving a sorting problem, which is, again, sort of, although in theory in the same order as the sort of synchrone algorithm, in practice this is always going to be kind of much, much quicker. So the point here is that 1D essentially is really quick, and in high dimensions you kind of have to do something much slower. So what people want to do is say, okay, well, let's just, if you have like a d-dimensional problem, let's just look at this over slices. Okay, so they define like the slice Wasserstein distance, which is, so you take a measure which is on the hypersphere. Okay, so then you project. Okay, so theta dot is the projection onto a 1D line. So in the slice Wasserstein distance, it's just going to be the integral over all the directions of the 1D slices of mu times mu. Okay, so if I have my mu and my nu here, and what I do is now I pick my direction theta. Okay, so then I project my mu onto this line here. So let's say I end up with PDF looks like this. Do the same thing for nu. So my PDF perhaps going to look something like this, and then I just compare the 1D slices.
and then I do this over all possible sort of angles. Right, so the motivation for doing this is that
instead of considering like marginals, you consider random slices. Is that the point?
yeah, exactly. So the point is that yeah, if you just take one sort of slice, it becomes like a 1D. You have like a 1D measure. So this theta push forward of mu, right? It's a probability distribution on R. So this sort of inner integral here can be solved very, very quickly. Now the problem is like how many. In theory, of course, right? You define this so you take the integral over all possible slices. In practice, of course, numerically you just take a set of slices. But of course, you can kind of see if the dimension is very large, then you potentially need a lot of different slices to kind of cover. So for something like in 2D, right, you can cover the circle fairly easily. But then of course, once you're in 3 dimensions and you're having to do this on a sphere, right, and you have kind of cursed dimensionality coming in. But okay, at least it's something you can kind of control, right? You can always just take kind of fewer slices and
there's some sort of heuristic of how it scales exactly the dimension, like I don't know how you could choose it just as an initial value.
Well, I guess you would. So I mean, I guess you can completely control it because I guess you just choose how many slices you're going to take. But then okay, I guess it's probably the number of slices you probably should take. Yeah, it should scale exponentially, I guess, with the dimension. If you want to kind of keep the approximation, but you can also argue that so this slice Wasserstein distance actually doesn't really behave. It's kind of quite disconnected from the Wasserstein distance. It's not that the slice Wasserstein distance is an approximation of the Wasserstein distance. So somehow once you're sort of discretizing the slices, you're sort of what you're trying to approximate anyway. So I think you kind of get away in general having quite a few slices. Okay, the point now is that the slice Wasserstein distance itself is is still a metric.
So there's basically no relation towards the sliced Wasserstein distance and the Wasserstein distance. Nothing like one bounds the other or anything like that.
I haven't thought about it in terms of bounds. I don't know. I mean, I guess I don't know. I've not seen it, but my guess is there probably isn't. But that's just a guess.
Okay. Can you pick the sigma to get back to the Wasserstein distance?
I don't think so. I'm pretty sure you probably can't. Yeah, it's kind of like I think there's also kind of no way to kind of connect. Okay, so inside the integral here, right, you'll have your optimal transport maps. Right, I don't think there's any way to get to construct an optimal transport map on the full space from optimal transport maps inside of here. I think it's Okay, so the next sort of special case is discrete measures. Okay, so here I'm going to assume that I have, so my mu and my nu are just n Diracs and they're all equally weighted. Okay, I assume these points here I guess are also unique, just to avoid problems like mass splitting. Okay, so then in this case here, what I have is that my optimal transport map is itself can be seen as being a permutation. Okay, which I think is natural. Okay, so first of all, this exists, which is not covered kind of by Arrhenius theorem before. Okay, and it's a permutation. So I think here, I just say that the optimal transport cost. Okay, so it's achieved for some pi dagger. Okay, and it's equal to some permutation. I think I sort of put the proof down in a couple of steps. Perhaps I just sort of skip over this more or less. Okay, so I think semi-discrete optimal transport might be the last part of this sort of section. So right, okay, so in semi-discrete optimal transport, we start off with some measure mu. So this has a density rho, but our target measure here is going to be discrete, right? So this is the semi-discrete, so we have a continuous and a discrete measure. Okay, so I want to define a Laguerre diagram. So the Laguerre diagram is defined using two sets. So first of all, you need a set of points and you need a set of weights. Okay, so then you would
Yeah, so I guess, okay, so in my notation, I tend to just like hide the set of points, but I just have the W represents so W is the vector of all the weights. Okay, so the sort of jth part of the Laguerre diagram is just going to be the points x, which are closer to yj than they are to any other point. I'm sorry, there's an absolute value here that's square missing here as well. Right, so first of all, if my weights are all 0, right, this is just the Voronoi sort of cells, right? So all I would be saying there is that if x is in the jth Voronoi cell, then x is closer to yj than it is to any of my other points. But by putting these sort of weights in here, right, I kind of allow things to kind of shift a bit into.
So is y meant to be like the center of the cell, or?
Yes, it can be. So okay, so it's yes and no. So in a Voronoi cell, right, yes, it would be the center of the cell. But actually, in the Laguerre diagram, it's even possible to have like for yj not to be in its own cell. Right, so you don't always get that. So it's slightly hard, I guess, to sort of gives a sort of intuition around that. But yeah, but it doesn't. You can have, if the weights again, in some cells are very big, yeah, then y doesn't appear in its own cell. Okay, so I also want to define this function g. Okay, so I take a gamma. So gamma here is essentially just going to partition my space Rd. Right, so for every point in Rd, I'm going to give it a number 1 up to n. Okay, so then I define my sort of g, which is going to depend on my sort of partitioning gamma and my weight w. This is going to be the integral of Rd of x minus y. Okay, so if I look at what cell I'm in, right, then I take the difference between x and the. Okay, I'm going to use the term center of that cell, although it's, with the caveat that it's not necessarily in the cell. Okay, minus wj, and I integrate this with respect to rho, and I also add on the sum of the weights multiplied by this masses mj. Okay, where these mj just came from the from this nu. Okay, and define now my little g as being the smallest value this capital G takes over gamma. Right, okay, so so my next comment is that each of these G's, okay, so if I fix my gamma, right, and I just look at my W, right, this is an affine function, right? So essentially, we're basically linear in W. Okay, so when I take...
We're doing this to construct the Laguerre diagram. Is that why we're doing this?
So where we're going, so the Laguerre diagram is actually, this collection of sets here.
Okay.
Where we're going with this is that this is going to actually end up being the same as an optimal transport problem.
Oh, small g, lowercase g.
Yeah, so we're going to end up, so this, the optimal transport problem essentially is going to be, we're going to be able to write this, as a, in terms of this g. Okay, so I just wanted to sort of make the comment that, okay, because this sort of capital G is, affine, okay, so it's concave. Okay, so when we take the infimum over a collection of concave functions, right, we end up with another concave function, right? So this little g here is concave. I also want to make kind of like I guess a relaxed sort of derivative. Okay, so relaxed sense I'm not really being sort of rigorous about this. But if I just differentiate g with respect to the weight wi, right, then okay, what I get is that okay, so this doesn't depend on wi at all. So I end up with just the integral of sort of rho of x, okay, over the set where this is kind of in play, right, which is exactly the ith Laguerre set, and then here. Again, so exactly so this is this term here because the x have the minus sign. here, and then okay, when I differentiate this with respect to y, then of course I just get mi out here. So I just get mi minus the integral of the Laguerre set. Okay, so this now is just mi minus the mass of the Laguerre set. That's okay. So you can perhaps now even sort of guess where this might be going. If I'm sort of optimizing this g over w, then I'm going to be setting this here equal to 0. So I'm going to end up, my optimal weights are going to end up being where the measure of the Laguerre diagram is equal to the mass mi. So this suddenly now starts to look like a mass conservation property. Okay, so this is kind of what the following theorem says. So we assume that w maximize g. Okay, so g is a concave function, right? So it has a maximizer. Okay, so I define my t dagger. This is just going to be the take the point x to the center of its Laguerre diagram. Okay, and if x is in the Laguerre diagram, is in the jth part of the Laguerre diagram, then I define my psi dagger of yj as being equal to the jth weight, and here I take my psi dagger as being the distance. I guess the distance to its closest Laguerre. Sorry, the distance to the closest sort of center. Okay, squared minus the weight. Okay, so with these definitions of t dagger, psi, and psi, t dagger is the optimal transport map with the quadratic cost, and this psi dagger and psi dagger maximize the Cantor-Rich dual with quadratic cost. Okay, and the proof is relatively actually kind of straightforward. So another mistake. Okay, so obviously derivative. Missing here. Right, so if my W are optimal, right, then I know that the derivative of G with respect to Wi is 0. Okay, so I have the mass conservation. Okay, so if I now look at what the push forward of T of mu at the point yj. So, okay, so this is going to be a measure on on my space y. Right, so this is just a set of okay, so it's the measure under mu of x such that t dagger of x is equal to yj. Okay, so this now exactly is the measure of the ith Laguerre diagram, okay, by construction of my t dagger. Right, and then because it's optimal, right, then this is going to be equal to mj. Okay, so my t dagger. Okay, so and this. Okay, so by my mj, okay, was the mass at the point yj. Right, so I know that t dagger push forwards mu onto nu. Okay. I can also check that my phi satisfy the optimality conditions. So if I just sort of write in what my psi here was wj, okay, and then my phi was just the rest. So of course, right, I can make this bigger by choosing a particular I. So I choose I being equal to j. In which case, yep, so there, yes, then the weights cancel and end up exactly with this here. Okay, which was just so this was all with quadratic cost. Okay, so this is true. Okay, so now this comes to the key part. So if I look at the dual cost, right, this is just, well, by definition, right, it's going to be, the first part is the integral with respect to mu, okay, which is the integral with respect to the density rho. And then the second part, okay, was the integral with respect to nu. Okay, nu is a discrete measure, so this is now just going to be a sum weighted by mj. So now I can sort of, instead of integrating over the whole of RD, I can just write this as a sum of integrals over each part of the Laguerre set. Okay, and then here, because I know my mass mj is just the integral of rho over the jth Laguerre sort of set. Right, there I can write everything kind of as the sum over integrals over each Laguerre set. Okay, so here now, yeah, I guess we realize this. So this psi dagger here should be side dagger yj. Right, okay, so then what I've used here is that side dagger x plus side dagger y is equal to, so actually I think I can probably get away with just saying this is less than or equal to here. So I can't quite now see why I get the equality, at least at this point. Yeah, okay, but then this gives us the, okay, this yj here by definition was just equal to t dagger of x.
But what do you do in the first line?
The first, this to here.
Yeah.
So this actually just is
No,
literally
I think not the equal, the second line.
this one here.
Yeah.
All I've done here, I think, is I've broken up this integral here as being the sum of the integrals over each Laguerre part, because each of these parts are okay up to like the boundary. I guess we have like a density, so I can throw that away. Yeah, and then I've used the fact that mj is equal to the integral over.
Right. Okay.
So I suspect, okay, if it turns out we do need equality here, then I'll go back and try and change it. Yeah, try and work out why. I said this, but I think at this point here, I want to relax this to being a greater than or equal to sign. I think that'll be enough. Okay, so what I have, of course, right, is that this this is a candidate map. So of course, it's going to be bigger than the infimum. Okay, so this itself is okay, going to be less than or equal to this. So this again is just from these. This is the Marne form. This is the Kantorowicz form. So I can always make things small by going into the Kantorowicz form. Okay, and then this by duality is equal to the supremum. Okay, so if I choose a particular side dagger and side dagger, right, then of course I make this smaller again. And then this from the previous side, so now let me, so this is equal to, but I think, so yeah, I guess I wanted this to be greater than or equal to, which, okay, it's not what I would have here. I think it's partly the other way around. So, okay, so this has to be equality. And so the reason why okay, I think it's just going to follow exactly from my side dagger on my okay, so yes, I've perhaps gone a little bit too quickly, but I think the equality should follow exactly just from the definition. So this side dagger x, okay, is so when x is in the J Laguerre set, right? This just means that this is exactly the set of okay, which achieves this sort of minimum here, right? So I think it does follow directly from that, but I think this is an equality here, which means that I can write equality here, and then going from sort of the left-hand side here to the right-hand side, right? So you have the same thing. So all these inequalities are in fact equalities. Okay, so this then means that in particular, like this T dagger here has to be the optimal one. So I think I've got one slide on sort of sort of extensions to these optimal transport spaces. So the first thing I wanted to mention was like the sort of TLP distances. So one problem with optimal transport, if you're applying this in practice, is that you need your underlying signals to be probability measures, right? So this means they have to be positive, they have to be single channel, they have to integrate to unity. Of course, right, this is not going to be true in sort of many cases. I mean, if you just take a picture, right? So a picture, okay, so already if this picture is in color, right, you can think of this as being sort of 3 channels sort of RGB, or whatever space you're working in. So of course, right, you can't do that. Okay, maybe then you go to sort of grayscale. But then, okay, so if you want to interpret this as a probability measure, right, this grayscale image would have to have, integrate to unity. So if you just take 2 sort of pictures, right, I mean, what's the chances that they're both going to have the same amount of, the same number of sort of, black pixels, right? So it's not true. And so, of course, right, you can do things like sort of normalization, but normalization can kind of, it can suppress features, for example. So, I mean, if you're normalizing, well, okay, so like a big, if you end up with a signal, say that's something like, say something like this. Okay, so it's negative. So what you'd have to do if you want to normalize this is you have to kind of shift everything up and then divide through by the amount of mass, and what you sort of end up with is something that kind of looks like, okay, so you shift and you get like that, and then when you normalize, you're going to end up with, I guess, something that looks more like that. And so you kind of suppressed, maybe. Right. So you can see anyway, somehow, you've kind of, everything's now sort of much sort of smaller sort of range than it was before. So the idea of the TLP distance is essentially to apply this to the optimal transport framework, but at the level of functions, right? So you actually look at your signals being a function, but then you still have this sort of Lagrangian way of sort of rearranging things. And I didn't go further into it than this because I guess I didn't want to sort of go off in too many sort of tangential directions. But I'm quite happy to kind of talk to people more if they're kind of interested in this thing. And the next sort of extension is sort of this linear optimal transport framework. So the idea behind this is to, okay, so another problem we kind of have is that if you give me a big data set full of images, right, and okay, so first of all, if I want to compute pairwise distances between all these sets of, between all these images, that's potentially sort of, in the order of n squared calculations I have to make. Each of these calculations is quite slow, so it's going to take me a long time. The second thing is that once, I don't have any, how do I do something like principal component analysis or k-means clustering in the Wasserstein space, right? I mean, it can be done probably, but it's going to be difficult, right? Certainly I'd have to kind of write my own code for this. I can't just call up a Python toolbox, but I can do this for Euclidean distances, right? So, Python will easily sort of let us code, let us do, PCA, LDA, k-means, whatever we kind of want. So the idea behind the linear optimal transport space is to find an embedding such that the Euclidean distances between signals is approximately equal to the Wasserstein distance between signals in the kind of the original space. So this is kind of what it means is that we can, instead of working with the sort of, working in a Wasserstein space, we can work in Euclidean space, but we still kind of get approximately the same geometry. So how this kind of actually works is that we project the signals into the tangent plane in the Wasserstein space, and so then we do everything in the tangent plane. So the idea being, if the manifold doesn't have any curvature, right, then the distance in the tangent plane is exactly the distance on the manifold. Okay, of course, the Wasserstein space does have curvature, but still what we have is, when we pick our reference point, we know that the Wasserstein distance between the reference point and our image is exactly equal to the distance of the Euclidean distance in the tangent plane of this projection, okay, with the reference. Okay, then okay, we kind of make the approximation that if you take 2 different points in the Wasserstein space, that their distance is approximately the same as the distance on the in the tangent plane. Okay, and what this kind of means is that we reduce from having to do n squared optimal transport calculations to essentially computing this embedding and then doing n squared sort of Euclidean calculations. Of course, Euclidean calculations are very cheap, very easy, so that's kind of get that for free. And then once we're in this Euclidean space, we can do use our favorite sort of tools. Okay, and then that's when it's got this sort of unbalanced optimal transport. So again, if we have sort of two measures which have different amounts of mass, then a natural way to sort of extend this framework is to allow for mass to be created and destroyed. So there's some sort of very nice theory. So there's things like the Hellinger-Kantorowicz distance, which allow mass to be created in sort of various sort of ways, but with some sort of penalty. Yeah, and sort of several people kind of worked in this sort of direction. Okay, so it's basically just pictures from here to the end, so you can sort of relax now. So yes, okay, so this is an example. Okay, so there's two data sets here. So this is a data set of cells, and this is a data set of faces. So I'll just describe the cells to start off with. So this is actually is describing the linear optimal transport sort of framework. So I don't know how many sort of hundreds or thousands of cell images there were in this data set here, but what the authors in this sort of paper did is they chose a particular sort of reference image. I think they kind of computed like the average sort of cell in just like in Euclidean sort of sense. And then they found all the optimal transport maps from this reference cell to all the other cells. And this sort of transport map is essentially the tangent vector. So they then sort of looked at this in Euclidean space. So looked at all this the possible transport maps from this sort of reference image of all the other cells, and then they could sort of throw their sort of Euclidean data analysis techniques like this. So the first thing they can do is they can find what the average cell is. So this turns out to be kind of the average cell here. So it's just it's kind of like a grey, roughly circle blob. And then in the sort of this linear space, you can look at the sort of the principal directions. Okay, so if you use the PCA, what you find is that the principal component is given by the sort of this top row here. So this is sort of shooting sort of one standard deviation to the left, one standard deviation to the right, two standard deviations, three standard deviations, four standard deviations. So what you can kind of see is what the kind of the biggest mode of variation in this data set is. If you look from here to here, you can kind of see, it's not particularly clear on the screen, but this cell here is kind of a lot bigger than this cell here. So what it says is that the biggest variation in the data set of cells is size. It's probably even clearer to look at the second mode of variation. Right, so here you can kind of, if you look at this cell here and this cell here, right, you can kind of see that one is sort of on its side, one is standing up. So the second mode of variation is kind of skewness, so which direction you're skewing. Then the third mode of variation is where mass is concentrated. So here mass is concentrated right at the center, here mass is concentrated right on the outside. Okay, and you can do the same thing for sort of for faces as well. Okay, so for data generating, right, so actually I regret now maybe not spending more time on the linear optimal transport stuff. So if you sort of imagine that this is the sort of Wasserstein space, the idea behind this was to sort of approximate these sort of this sort of image manifolds at various different points and try and use that to then sort of generate sort of new images. Okay,
can I stop you 1 second? Like, can you give me a bit more of an intuition of this Wasserstein space, like what it means? Because right now I'm thinking about like Riemann manifolds from like MCMC and so on. It's probably related, but not quite the same. Like, what does? So, what kind of space is that in an intuitive kind of work? Could you maybe say a bit more?
I guess it's. So the easiest probably way to describe it is probably to go back to the very first example where we just had this sort of these balls that are moving. So I mean, I guess it's the Wasserstein space. I guess it's the space of probability measures and band-repeat moments with the Wasserstein topology. So then, okay, so the question then really becomes, okay, what is the Wasserstein distance? What is that kind of capturing?
So every point is a distribution, and then
Yes, it's So it's
Okay.
it's a metric on the space of probability measures, obviously.
Okay.
So we are in the setting where we're not. So these are infinite. This is still an infinite dimensional space, right? So what's the manifold, I guess?
It is, okay, so I guess we're, yeah, it's okay. So sometimes we're in an interdimensional setting, but I guess so in this setting here, the idea is, okay, we're in infinite dimensions, but we're actually not really using all of these dimensions. So how this sort of worked is if we imagine our, okay, so I can't draw in infinite dimensions, so I just draw in 3 dimensions. So we pick our points here, right, and then okay, we draw kind of our tangent plane. So you imagine we kind of have lots of sort of images which all live on this sort of manifold, and then we sort of project them up into the tangent plane. So I guess, okay, so the reference becomes like 0 and everything else. So then what we get now is have in the tangent plane, it is just, maybe it starts to look something like this. Okay, but because these are points now in just Euclidean space, we can start to do things like, so the way this worked here is that we fitted a Gaussian to them. So, we just look at the sort of the principal component, right? We fit a Gaussian in this direction, the second. Okay, you end up with fitting a Gaussian something like this. So how is the generated data now is that, so so I guess here we were approximating the Wasserstein's manifold at 5 different points. So if we wanted to generate a new point, we choose one of those 5 points. We then choose we sample from the Gaussian at that point. So maybe we pick a new point here. Okay, so that gives us some points, I guess somewhere around here. You project this back onto the Wasserstein space, and then that gives us a new sort of image. Okay, so we did this with faces. So this top row, there should be 19 faces there, and these are all kind of real images from some data sets.
So in the reference image, so you need a reference, right, before doing.
Yeah.
What's it like an average of?
Yeah, so I think so. In all the experiments I've done, it's never really seemed to matter what the reference image is. So I think whenever I've done it, it's always either kind of been like, yes, the average, but normally actually the average in like a Euclidean sense. So so we literally just pixel by pixel, just do it. I mean, the other way to do it is to look at like the first.
So it doesn't look even a face, right? If you take the.
Yeah, it can be a bit sort of blurry. A bit.
Yeah.
Yeah. I mean, there is so theoretically there is an optimal choice, right? That's to choose like the Wasserstein barycenter. Okay, but the problem then is you have to compute the Wasserstein barycenter. Essentially, we found that it's not worth doing. It depends, on how curved the space is. So of course, right? Yeah, if all your points are here, and you choose your reference measure to be over here, right? Then your tangent plane is going to be kind of a terrible approximation at these points here. But we seem to not really ever find this.
So the gray image there, I'm wondering what it is.
Yeah, so this I guess is the representation of I think it's probably like the velocity field, and the velocity field, right, is the the tangent vector, and then from that you can get back the optimal transport map. Yeah. So anyways, so in this set here, we have 19 images, right, and we use these sort of. So I think you just have like one cluster here. So essentially, we do our embedding, and we fit a Gaussian using 19 images, and then we sample 38 new images, right? And so the second and third rows are kind of the samples. Okay, and it's it doesn't work too badly, I think. I mean, these it doesn't show too well on the screen, but most of these spaces they kind of look fairly realistic. And of course, because we use so few samples, you can actually check that we haven't just sort of we're not reproducing anything in the training set. I mean, there's a few cases right where it doesn't go too right. You can see this guy here, the lips are kind of a bit funny, but in most cases, from 19 images, right, it doesn't do too badly. And
sorry, random question: if you with the Gaussian, happen to sample a point that when you project it, falls near to an image you already have. Can you tell that they're actually similar, or the original image and the image you sampled close to the original image?
Yeah, they should be. But okay, so we didn't sort of test this sort of numerically, so I don't know. But it does. I mean, in terms of the Wasserstein distance, you can have like quantitative bounds on this. So I forget. So the Wasserstein space has negative curvature, right, which I think you can show quite easily, just because. Yeah, if you look at the distance between 2 points, you can sort of a candidate map. Right, so if you have this point here and this point here, right, a candidate map is the map that goes from here to here, then here to here, right? It may not be the optimal one, but okay, that then the point I guess is that gives you like in the Euclidean space, right? That's kind of the that's the distance between these 2 points here, right? It's just the distance between the two vectors, and that kind of gives you an optimal. That gives you a map, which may not necessarily be optimal. So it kind of gives you like a bound on the Wasserstein distance. It's much harder to get the other bounds right, and it's not. Yeah, it's something kind of funny anyway. It's not like the topology isn't equivalent. Is what I'm sort of trying to say. Is you end up with showing something like. I'm probably wrong with this, but if you define like the sort of linear Wasserstein distance, mu nu, I think this is something like above, I think some constant, the Wasserstein distance between mu and nu to some power. It's something like, I would say something like 5, 6 or something like that, or but yeah, so there is kind of a way to kind of say, okay, yeah, close in linear space, close in Wasserstein space.
Can I also ask you, are you using gray images because of a computational reason, or because you're bound by one-dimensional kind of?
Because we're doing this with Wasserstein distance, yeah, we can't. So yeah, so essentially we need to be able to treat all these faces as probability measures. So yeah, so we can only have, it has to be sort of grayscale.
You could use the 3 red, blue, green.
The problem then is, yeah, it could be. So what you're saying is that you could do it 3 times.
Yes, again on the product space of red, blue, and
Probably
green.
the 3 slices.
Yeah, I don't know exactly. So the problem I guess then is that you kind of your transit maps would all be kind of decoupled.
Yeah.
So I don't. Yeah, I mean, I guess okay. So I guess yeah, I don't know what happened if you kind of then just put these RGB channels all together afterwards. Yeah, I mean, I guess maybe
it's a common technique when you
right.
want to read color images, right? Or like to just.
So yeah, I have.
Maybe for later.
Yeah, so I guess I had this. So I can't remember now actually what the. So. Yeah, so okay, so there is a way. So this is okay. So this is the problem like color transfer. So the idea now is you have like an image and you want to transfer the palette of another image here. So if you just do this during optimal transfer, I can't remember that. Maybe this is done how you sort of said, but just doing like RGB channels separately. You don't get too good a solution anyway. But okay, so this was from a paper which is TLP framework, which is essentially an optimal transfer on the level of functions. Okay, and the point is actually get a kind of a much better sort of solution with at this level. So okay, so yeah, definitely you can use optimal transfer.
Yeah.
My experience is that it doesn't work quite as well. And,
Okay.
Yeah, this is another sort of color transfer problem.
Question that was slightly different, I guess. What is the computational, like how expensive is it to actually do these computations?
So I think someone better than me is going to talk about this sort of numerics later this week. But yeah, it is pretty slow. So people are kind of very excited about it. The synchron algorithm. This is kind of it's faster than what you had before. So trying to solve the linear program, right, is kind of really slow. It's not really feasible. With like the synchron algorithm, I think you can probably you get comfortably to like maybe 256 by 256 images, you know, waiting like a little bit. If you know, maybe if you have like a very good implementation, probably 512 by 512. I'm not sure you can really go much.
Are we talking like minutes, seconds, hours?
You can probably, so, okay, so when, yeah, I would say probably in the order of minutes for, but I would, you know, someone else might disagree with that. Okay, my coding also is very bad. So for me, it gets like 512 by 512 probably takes a couple of hours. But I feel like probably, you know, there are better codes out there that can do it quite quickly. But yeah, but it kind of becomes quite quickly in, see, obviously it scales really badly with dimension. And then, yeah, and so yeah, if you have like a big data set, you can't really wait 5 minutes to compute the distance between every sort of pair. So yeah, so synchrony, I guess, is like people's favorite methods at the moment, but it's still, it's big improvement over linear programming, but it's still kind of slow and a problem. I think I skipped one out. Yes, this again was another sort of application. So this was example like so a highly multi-channel signal. So this was like a data set called the Ausland data set. So this was someone who wore these sort of special gloves and then sort of spoke in sign language. So the yeah, so I think there's 22 sensors on these gloves, and okay, so the signal itself is, you know, goes from, I guess, like time being, you know, between 0 and 1 into some sort of 22-dimensional space. And the point is, you know, we can kind of, there's a way to kind of do this in the sort of optimal transport sort of setting. You know, you can, and you can, you know, if you're classifying the sort of words, quite, you can get sort of around sort of 80% accuracy over sort of 27 different sort of classes, which is kind of sort of reasonable. Right, I think I'll. So obviously, there's kind of sort of no details into any of these applications because I think to do it would be, you know, it would take sort of too long. But I've also applied this sort of framework sort of to medical images. So again, you know, the key idea here is, you know, we take an image of a, so this is sort of a lung image. We divide it up into sort of patches. For each patch, we kind of compute this sort of embedding, which is just this sort of, you know, yeah, this sort of linear optimal transport embedding. So essentially, it's the transport map. Okay, and then this sort of, okay, then we sort of stack all these sort of transport maps together. So each sort of, yeah, the map from each patch essentially, and then this gives us a way of sort of, you know, classifying, you know, sort of a very long vector, which corresponds to how things get moved around. Okay, so here, you know, of course, this was done during the COVID pandemic, so we're kind of looking at sort of, can we calculate the difference between sort of healthy and COVID patients, and, you know, up to about sort of, yeah, I guess 83% accuracy. We were, you know, we were kind of right. I believe like there's someone trained a neural network on the same data set, and I think we pretty much beat them, which is sort of, yeah, quite nice.
So dividing into patches is again, because it would be too hard to.
Yeah, so it was kind of done for two reasons. I guess like one, yeah, I guess because it's too high dimensional. But the second reason actually was, so there's a kind of step which I missed out here, and that's that a lot of the patches, like between healthy and like, you know, and unhealthy patients are going to be the same, right? So I mean, particularly, you know, the regions around the, you know, the edges, and even like you can imagine someone like very unhealthy might have one lung that's really healthy, one lung that's really not. So we kind of wanted to kind of compare this sort of more locally. So the idea then is if we look at patches, then we kind of, we let each patch sort of cast a vote. So actually we try and classify this at the level of patches first of all. And then so each patch says, okay, I think I'm healthy, I think I'm unhealthy. So even a healthy patient would probably expect the majority of patches to be healthy. And then sort of, you know, once all these patches have kind of voted, then we kind of collect overall. Then we say, okay, if more than, I think, you know, like 40% of patches have voted for unhealthy, then we say unhealthy, and otherwise, you know, we say healthy. And that was kind of
And it's robust on rotating, shifting, or making the image larger or smaller. I mean, people have different chests, right?
Yeah, I guess it should be. Yeah, I mean, we didn't sort of test this sort of robustness, but I would kind of hope it would be. I mean, like it's because I guess it's a more geometrical, you know, sort of, yeah, sort of pipeline than it is like for like a neural network, right? You have no idea what you're kind of learning. So it's,
Okay.
Okay, and this is okay. Yes, make explain. So, final example. This is again just using this sort of linear optimal transport for sort of particle decays. So the idea now is we have two different types of particle decays. So I always forget which one's which. One of these are W bosons, and the other ones are QCDs. Let's say these are W bosons, where you typically have sort of two big particles and surrounded by sort of lots of small particles, and then the QCDs where you have sort of one big particle surrounded by lots of little particles. Okay, if you use linear embedding, you end up kind of, the best 2D approximation is this sort of picture here. Okay, so what you can kind of see is that you get most of the sort of W bosons around here, with like a small number around here. And actually, it's quite reasonable that you get this sort of small number here, because if you look at kind of a typical example at this point here, it is just one particle. So what's probably happening here is that the two particles here are kind of on top of each other. So the size of the particle here actually represents the energy of the particle. So this is probably actually two particles that just kind of land at the same point. And so the energy is kind of twice as big. So it looks like a QCD, but actually the W boson. Okay, so then I just had some references. Okay, and that's everything. So I guess thanks for listening. We started half an hour late and we finished 28 minutes or 27 minutes late. So.
Perfect time. You mentioned that the synchrone complexity was n log n, isn't it? N squared.
You could be right. I tried to quickly look this up, and I thought I read. I was surprised. I looked this up, and I'm sure it said n log n. I'm sure I was surprised about this because I thought it was going to be worse than that.
So I guess you have projections on the matrix that will be you can compute the whole cross matrix.
Yeah. Okay. Yes, that could be. Okay. My source was n log n, but I might have misread the source, or the source might have been wrong. So I'm quite happy to be corrected on that. So.
In this case, n is the number of, because you are dealing with discrete measures, right?
Yeah. So n, I guess, is the number of particles you have. Yeah. Yeah. So then, typically, I guess if you're discretizing a measure, then I guess n will probably typically depend exponentially on the dimension of the space. Yeah. So. Yeah. So.
Okay. And people usually take a discrete, like a regular discretization, homogeneous.
I guess most of the times, well, I guess it's often sort of images that people are applying this to, in which case, the discretization is exactly, like the pixel locations. So, so in that case, it would always be regular. Okay. Although there is, sometimes, so I've started using some point clouds, for example. So then, of course, right, it's not a regular discretization. And so, I guess typically people either do it on point clouds or images. So it's not always uniform, but often is.
So I have, I guess, two questions that are separate from each other. The first one is I noticed that there's a lot of theory for when you take the special case from the cost function theory. Is that just because of practicality, or is there, like, the intuitions also translate oftentimes to other things, or like is the computation become a lot more challenging?
So computationally, I think most times it doesn't really matter. I mean, like things like the synchrone will kind of work with anything.
How about the theoretical here?
So when you say, so in terms of the theory, then you don't have any of this, so like the formal Riemannian structure, right? This is very specific to the case P equals 2, and the Benjamin-Brenier fluid dynamics formulation, right? This is also very specific to the case P equals 2, right? So this doesn't, so for an arbitrary cost, none of this sort of this works, but beyond that, I mean, things like like the Knott-Smith optimality, criterion, Brenier's theorem, right? These are all kind of generalized to sort of more general costs. I mean, most things actually are kind of pretty much exactly the same. There's sometimes like slight difficulties, like the P equals 1 case. So actually Monge originally proposed optimal transport for the case where it just x minus y in absolute value, no power. And this actually is probably one of the hardest cases, but mostly there isn't too much difference.
Can you know, like, okay, so can you talk about any relation between like Fisher information, like geometry, because that's another canonical geometry composed in this distributions. But that's, I think there's this thing called Chestov's theorem that basically says that that's the only Riemannian metric you can impose on the space of probability distributions. That's invariant to reparameterization of underlying state space.
So this is not something I know very much about. The only thing that the only place this is ever kind of occurred, like, which I've kind of looked into, is in the Hellinger-Kantorowicz distance. So in the Hellinger-Kantorowicz distance, this is like a generalization of the Wasserstein distance to where you have a sort of unbalanced measures. So you allow for mass to be created and destroyed. And the idea now is that instead of having the continuity equation in your fluid dynamics formulation, but you kind of have like a mass creation and destruction term. So then, of course, right, so on the transport, right, you have the kinetic energy to penalize. Then, of course, you need like some sort of penalty on the mass creation and destruction. And this is now where you would use your, so I think it's, like the Fisher-Rao distance, right? So this is the unique parameterization invariance, sort of, Riemannian distance. And in that case, and then so this particular choice actually gives you the, a nice sort of Riemannian structure still on the Hellinger-Kantorowicz. Sort of space.
Look very different in both, like the ultimate and Fisher. So I guess I've always been trying. This is one of these things I've been trying to figure out. Like, when should I be thinking of one versus the other?
Yeah. So yes, I mean, other than that, I don't actually know anything really about the Fisher-Rao. It's like I don't know how it would. Yeah, I mean, I guess it's not really a Lagrangian. Yeah, so it's not like, I don't think it's a Lagrangian sort of base distance. So I guess it's probably more similar to L2 than it is to sort of like, Wasserstein. But I can't really say anything else.
Yeah. All right, so thank you very much. For the people that are checking in at Radcliffe, the hotel is just 5 minutes walking distance from here. You can check in. We have a dinner reserved at 7 o'clock, so we can meet at the lobby of the hotel at around 7. And I think that's it. Okay, see you later. And if you want to stay here, I will be here until for another hour or so. I think the common room or around. Right. Thank you. Thank you.
One second here too. So.
Thanks for a nice talk.
Oh, yeah.
The heroic 3-hour effort.
I was getting tired towards the end.
I've never seen like such long. Can I? This is just about my own ignorance. We were talking about the tangent, like space.
Yeah.